Welcome viewers, in this video we'll see the electrical quantities, basic electrical quantities. First we'll see the charge. The charge is nothing but a physical property of the matter that causes it to produce a force when an electromagnetic field is applied. Right? So it is a property. Charge is nothing but a property of the matter. When electromagnetic field is applied, it experiences a force. So in any object there are n number of electrons, protons and neutrons are available under normal condition. Electrons, proton and neutrons are available under normal condition. Electron is a, that positively charged, negative charge. Proton is a positive charge and neutral is neutral. There is no positive or negative. So under normal condition there is no the movement of electrons. If any external force is applied, then the atom will move from one place to another place. So while applying the external force, what will happen? The electrons are moving from one place to another place. Due to this movement, if number of electrons are less than the number of protons, then it is known as positive charge. The number of electrons are less, protons are more. You know that proton is positively charged. So the entire object is termed as positive charge. If number of electrons are less than the number of protons, then it is known as positive charge. Suppose if number of electrons are more than the number of protons, then it is known as negative charge. So if electrons are more, automatically it is a negative charge. So charge is purely based on number of electrons and proton. Under normal condition, there is no movement of atom. While applying any external force, the atoms are moving. Under that condition, if electrons are more than proton, then it is negatively charged body. If electrons are less than the number of protons, then it is called a positively charged body. So we are dealing with a charge that is purely depends upon number of electrons and protons in any object. Right? So while applying external force, what will happen? The electrons are moving from one place to another place. So this movement and number of electron and what is the energy, what is the power, everything coming based on the movement of the atom. Right? So that movement of atom is nothing but current. How many atoms are moving? How many atoms are available? That refers potential difference, energy and power. Now we'll see these terms one by one, right? So all other terms is purely based on the movement of the electron while applying external force. So next we'll see the electric current. So we already discussed, if any external force is applied, the electrons are moving. Atoms are moving from one place to another place. So the flow of free electron. So this electric current, the symbol is I. The flow of free electron in a conductor is called a electric current. Right? So the current is flowing. We are saying current is flowing. Current is flowing means the flow of free electron in a conductor. So it is defined as rate of change of charge, dq divided by dt. How much the charges are moving, dq divided by dt. Right? So the flow of free electron in a conductor is called a electric current. It is defined as rate of change of charge. The symbol is I equal to dq by dt. The unit is ampere. Right. So while applying external force, the free electrons are moving. That is nothing but a electric current. And how many electrons are moving? That we'll see the next. That is called electric potential or voltage. What is that? The ability of the charged body to do the work. How the electrons are moving, how many electrons are moving, that is a potential. That is the ability of the charged body to the work, either 10 electron or 100 electrons. We are saying I have the potential to do this work. I am able to take 5 books, I am able to take 10 books. That is our potential. Similarly, here potential refers the charged body to do the work. That is nothing but work done by charge. Work done by charge is nothing but a voltage. What is the charge available? How many electrons are moving? That is nothing but work done by charge will give the voltage. The unit is volt. Next we will see the potential difference. What is the potential difference? In one place the electrons are more, another place electrons are less. So the difference in potential of two different bodies is nothing but a potential difference. In one place 100 electrons will be there, another place 1000 electrons will be there. So there is a difference in potential, that is called a potential difference. Then we'll go to the power. What is the power? The rate at which the work is done in an electric circuit is called a electric power. What is the rate? So while applying any external force, the atoms are moving. So how many atoms are moving is nothing but a electric power, right? The rate at which the work is done. So I am able to take 5 books within a 1 second. I am able to take 10 books in a 1 second. So that is nothing but power. So here the rate at which how many electrons are moving is a potential. How many electrons moving in a given time, within a time, the rate, that is nothing but a power, right? So there now so many electrons are moving, 10 by 10 electrons are moving one by one. That's called a potential. That's a power, the rate at which the work is done. So the general formula is voltage into current. The unit is watts, right? So next we will see the energy. What is energy? So it is nothing but capacity of the charged body to do the work at a given time. So I am able to take 10 book or 20 book at what time? Either 1 seconds or 1 minute or 1 hour. That refers the energy. Energy always refers voltage into current, that is power into time. What is the power consumed in a given time? That refers the energy, right? So the electrons are moving. The ability to move the electron is nothing but potential. I am able to move this book. The rate at which how many books are moving, that is the power. How many books are you are moving for a given time is the energy, right? So the electrons are moving is a potential. The electrons are moving at a given rate, that is the power. The electrons are moving given rate for a given time is the energy, right? So the unit is joule. Next we'll see the charges. What is the general term for the charge? So 1 coulomb of charge equal to 1 divided by 1.602 into 10 to the power minus 19. This universally it is a constant. The 1 coulomb of charge is this value. So 1 divided by, so it is nothing but 6.24 into 10 to the power 18 electron. 6.24 into 10 to the power 18 electron. That is 1 coulomb of charge. Suppose a single electron have a charge, positive charge or negative 2 charges available. So minus 1.60 into 10 to the power minus 19 coulomb. Similarly, single proton, that is positive, plus 1.602 into 10 to the power minus 19 coulomb, right? So this is the 1 coulomb of charge, this value. This is one single electron having the charge and one single proton having the charge, right? This is negative and this one will be positive. We will see some more quantities with the symbol and unit. Now we will see this, the quantity, symbol, unit and formula for the further electrical quantities. First we will see the charge. The charge is symbol is Q. The unit is coulomb. It is written as C. That is nothing but current into time. The formula is current into time, right? The charge, it is termed as Q. The coulomb, the unit is coulomb. It is also written as C. The formula is I into T. Then next one is the current. The symbol is I. The unit is ampere. It is written as A. That is the formula is Q divided by T. Charge divided by time. Third one, voltage. The symbol is V. The unit is volt. It is can be written as V. What is voltage? W by Q. Work done by charge. W by Q. Then energy. The symbol is W. The unit is joule. We can write it as J. Power into time. The energy always refers what is the power at a given time. P into T. Then what is the power? Power equal P. The unit is watts W. W by T. The power is nothing but W by T. The next one, resistance R. The unit is ohm. The symbol is ohm. V by I. The formula is V by I. The capacitance. The symbol is C. Farad F. Q by V. The formula is Q by V. Next, inductance L. The unit is Henry. Q by I. Then frequency. The symbol is F. Unit is hertz. 1 by T. Then impedance Z. The symbol is Z. Ohm. V by I. Then admittance. Symbol is X. Ohm. V by I. So these are all the some electrical quantities we referred with the symbol, unit and formula. So in this video we discuss about the electrical quantities, definition of electrical quantities, then unit, formula, and some more electrical quantities also discussed with the symbol and formula. Thank you. Welcome viewers. In this video we will see the SI units. What is meant by SI unit? What are the units are available? We'll see in this video. The SI is nothing but it is the abbreviation of the French word Système International. The international level the standards are defined so that everyone need to use the same standard for the uniformity. Entire universe, in order to get the uniformity we have SI units. That is the abbreviation of Système International, that is from the French word. That is nothing but international system of units. SI is nothing but international system of units. Is the metric system that is used universally as a standard for measurements. In order to get the uniformity over the entire universe, these SI units are defined. So everyone need to use these SI units for representing the measurement. The SI unit plays vital role in scientific and technological research and development. In order to we have the uniformity, so that while going with any research and development, it will be very useful in order to go with the uniform standards, uniform units. So there are 7 base units are available and 22 derived units are available. The 7 base unit means it is a basic. There are 7 basic units are available. From the base unit, there are 22 derived units are available. And some more derived units also available from the base. By standard, we have 22 derived units. See, these derived units are obtained from the base unit. So, only these 7 are base units. All other units are derived from this base unit. So that it is called a base unit and derived unit. This SI unit can be expressed as either as a standard multiple or fractional quantities. Standard multiple or fractional quantities. These quantities are defined with the help of prefix multipliers with the power of 10, that is ranging from 10 to the power minus 24 to 10 to the power plus 24. Right? So these SI units are represented as standard multiple or fractional quantities. That is, what is that standard multiple and fractional quantities? That is power of 10 on both the side, negative as well as positive. 10 to the power minus 24 to 10 to the power plus 24. Right? Now we'll see what are the 7 basic units, what are the 22 derived units, and what is the range from minus 24 to plus 24, how the units are represented. That also we'll see in this unit, in this video. So base unit means a fundamental unit or considered as building block of the system. So this is a fundamental units. All other units are derived from this base unit. It is a building block. From that only other units are derived. So the derived unit means the derived unit is a unit of measurement in international system of units that is derived from one or more of the 7 base units. So only this 7 base unit is the building block for all other derived units. All other derived units are obtained from these 7 base units. Now we'll see base unit, derived unit and multiples one by one. First we'll see the SI base units. So there are 7 SI base units are available. We'll see one by one. The first one will be length. The unit is meter. The symbol is M. First one is the length. The unit is meter. The symbol is M. How it is defined? How internationally defined the length? It is defined by making fixed value of the speed of light in vacuum. Right? We know what is meant by 1 meter, 2 meter mean we know, but how it is defined 1 meter, what is internationally defined, what is 1 meter? We know what is 1 meter by seeing the scale or the tab, you are easily identify meter, but how it is defined internationally is nothing but taking fixed value of the speed of light in vacuum. That is a reference. 1 meter means it's a speed of light in vacuum. Right? So the first one is length, unit is meter and symbol is M, that is defined by fixed value of speed of light in vacuum. The second one, mass, kilogram, the unit is kilogram and symbol is kg. So while purchasing any product, any material, we are referring with kilogram or gram. So that is the second one, mass. How it is defined internationally? Defined by taking fixed value of Planck constant. From the constant only we define what is 1 kg. While going to shop, we can know the 1 kg material is available. But how it is defined by 1 kg is nothing but a fixed value of Planck constant. That is important, right? This is previous one, speed of light. This one, constant. The third one is time. The unit is second. Yes, we know that the time is measured by either second or minute or hour. The base unit is second. But what is second? By taking the fixed value of cesium frequency. The cesium frequency is the reference. 1 second. 1 second is defined internationally by cesium frequency. Right? So these are all the 3 standard. How they are defining also available. Speed of light, Planck constant, cesium frequency. From this we are able to know what is 1 meter, what is 1 kilogram, what is 1 second. We are able to easily identify. Universally we are following the same unit for these quantities universally. We'll go for further some more another SI units. The fourth one is the electric current. The symbol is I. Ampere. The unit is ampere and the symbol is A. What is how it is defined internationally? Defined by taking the fixed value of elementary charge. Right? The fixed value of elementary charge will define the current. From that we are easily measure this is 1 ampere, 2 ampere, 3 ampere. But internationally what is meant by 1 ampere is fixed value of elementary charge. Then thermodynamics, temperature, theta. The unit is Kelvin, the symbol is K. We know that the temperature measured in Kelvin. Another one Celsius available, but Kelvin is the base. How we are measuring this Kelvin? Defined by taking fixed value of Boltzmann constant. Since this Boltzmann constant will define the temperature Kelvin, 1 Kelvin. That is K equal to 1.380649 into 10 to the power minus 23. So that will define the Kelvin. The next one is amount of substance. The unit is mole, symbol is MOL. What is that amount of substance? How it is defined? Fixed value of Avogadro constant. So this constant, Avogadro constant, will define the amount of substance. Then luminous intensity. The intensity means the lighting. What is the intensity? The unit is candela, symbol is CD. We know that this bulb is very bright, this bright is less. We are easily telling the luminous, but it is defined by fixed value of luminous efficiency. From luminous efficiency, we are defining the candela. So these 7 are the very basic SI units. All other SI units are derived from these base units, right? So what are the things are there available? Length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. For all, symbol and units are available, and how it is internationally defined also, the details are available. Now we'll see the SI derived units. 22 derived units we'll see. All these derived units are available from these base units. Okay, now we'll see the derived units one by one. So this is the name, symbol, quantity, and SI base units. From which base unit we are getting this? That is nothing but SI base unit. It's a combination of one or more base units. The first one is hertz. The symbol is Hz. What is the quantity? Frequency. The frequency is measured in the unit hertz. It is represented by Hz. What is that? S power minus 1. The base unit is S power minus 1. Next one, angle. It is measured by radian. The symbol is rad, R-A-D. That is 1. The base unit is 1. For angle, we have one more angle, solid angle. Steradian, SR. Steradian, SR, that is used for solid angle. Normal angle referred by radian. That also, the base unit is 1. The fourth one, Newton. That is for measuring the force. The unit is Newton. Symbol is N. For force, but the unit is Newton. The symbol is N. What are the base units here? Kilogram, meter, and S power minus 2. This is nothing but second. S power minus 2. So see this, there are 3 base units are available to define the term force. kg.m.s power minus 2. Then for measuring the pressure, you have Pascal, PA. For measuring the pressure, the unit is Pascal. The symbol is PA. What are the base unit? kg.m power minus 1, s power minus 2. Kilogram, meter, and second. kg.m power minus 1, s power minus 2. It's available for pressure. We'll go some more. Next, energy. Energy, the unit is joule, represented by J. For measuring the energy, the unit is joule, it is represented by J. What are the base unit? kg.m square dot s power minus 2. Right, kg m square s power minus 2. Then power. For power, the unit is watts, watt, represented by W. What are the base unit? kg dot m square s power minus 3. S power minus 3 for a power. Then electric charge is defined, is given, the unit is coulomb. The symbol is C, electric charge. What is that? S into A. S into A is a base unit. Then voltage is measured as, unit is volt. The symbol is V. What are the base units available? kg dot m square s power minus 3 into a power minus 1. These are all available for voltage. Then capacitance is measured with the unit farad. The symbol is F. kg inverse m power minus 2 s power 4 a square. That is a base unit for capacitance. Then we'll go to the resistance. Resistance, the unit is ohm. The symbol, this is the symbol. What is the base unit? kg dot m square s power minus 3 a power minus 2 for resistance. Similarly, conductance. The resistance and conductance are inverse. Is Siemens. Conductance is given Siemens. The symbol is S. What is the base unit? kg minus 1. kg power minus 1 m power minus 2 s cube a2. That is for conductance. Then magnetic flux is the unit is Weber. WB. The symbol is WB. The base units are kg dot m square s power minus 2 a power minus 1. Magnetic flux density is given as Tesla. The symbol is T. Magnetic flux density. Tesla. kg s power minus 2 a power minus 1. Right? The base units are kg s power minus 2 a1. Then inductance. Inductance is the unit is Henry. The symbol is H. kg m square s power minus 2 a power minus 2. The base units. Then temperature in Celsius. Already in base units available as Kelvin, but here is Kelvin. Is and one more unit is Celsius. Right? The base unit is K. 273.15 K. Right? So the Kelvin available in base unit, Celsius available in the derived unit. The next one is the lumens. What is the luminous flux? Luminous flux, the unit is lumen, is CD, candela. Then illuminance is lux. The symbol is 1x. CD dot m power minus 2. Then another 4 are available. Radioactive decay per unit time. Right? So the radioactive decays. These are all based on the radioactive radiations. Right? Becquerel is the unit. BQ is the symbol. S power minus 1. Observed dose of ionizing radiation. Gray, GY. M square S power minus 2. Equivalent dose of ionizing radiation. Sievert, SV, S power minus 1 mole. Then catalytic activities. That is Catal, KAT, S power minus 1 mole. So these are all the 22 derived units. These 22 derived units are obtained from the base unit. Now we'll see the multiples and submultiples. That is 10 to the power minus 4 to 10 to the power plus 24 available. We'll see the terms one by one. So we'll see what is the prefix for multiples and submultiples. How these units are represented with the prefix. First we'll see the start from 10 to the power minus 1. Then we'll go to this. These are all negative. We'll go to positive later. First we'll see the negative. 10 to the power minus 1 is prefix is deci. The character is D. Right? D, deci means it is represented 10 to the power minus 1. 10 to the power minus 2 means centi, C. 10 to the power minus 3 means milli. The symbol is M. 10 to the power minus 6 is micro. The symbol is mu. 10 to the power minus 9 means nano, N. 10 to the power minus 12 means pico. The symbol is P. 10 to the power minus 15 is nothing but femto. The symbol is F. 10 to the power minus 18 means atto, A. 10 to the power minus 21 means jepto, Z. 10 to the power minus 24 means iacto, Y. So we can represent the units by using this prefix starting from 10 to the power minus 1 to 10 to the power minus 24 available. So we can represent using this. Similarly, the positives, the multiples also available. 10 to the power 1, 10 to the power 1 means deca, dA. 10 to the power minus 2, 10 to the power 2 means hecto, h. 10 to the power 3 means kilo, k. 10 to the power 6 means mega, m. So these are all multiples that are the previously what we did is submultiples. 10 to the power minus 10 to the power 9 is a giga, g. 10 to the power 12 is tera, t. 10 to the power 15 is peta, p. 10 to the power 18 is exa, e. 10 to the power 21 is zeta, z. 10 to the power 24 is iota, y. So here is the multiples available from 10 to the power 1 to 10 to the power 24. So in this video we discuss what is SI unit, what is SI base unit, what is derived units, and we discussed the 7 base units, 22 derived units, and also multiples and submultiples. Thank you. Welcome viewers. In this video we'll see the active and passive components. First we'll see the active component. An active component is an electronic component supplies energy to the circuit. So due to this it is called as the active component. This energy is supplied to the circuit. That component is able to supply the energy to the circuit. So what are the examples are available? Voltage source, current source, generator, all type of transistor, diode. These are all the example for the active components. They are able to supply the energy in the circuit. Now we'll see this one by one. First we'll see the voltage source. The voltage source is an example of active component. When current leaves from positive terminal of the voltage source, energy is being supplied to the circuit. So when the voltage source is connected in the circuit, the voltage source able to supply the energy into the circuit. So that's why it is called a active component. Similarly, the battery also considered as active component because it is continuously deliver the energy to the circuit during the discharging. Right? So the voltage source as well as battery are the active component because they are supplying the energy to the circuit. Similarly, the current source. Current source is current supplied by the supplied to the circuit by the ideal current source is independent of the circuit voltage. So the current source is controlling the flow of charge in the circuit, so it is classified as the active element. So the current source able to supply the current to the circuit continuously, independent of circuit voltage. It is always delivering the current to the circuit. So that's why it is called as a active element. Then the transistor. The transistors are able to amplify the power of the signal. So that it is also called as a active component. The transistor is one of the main component in the amplifiers. So transistors are able to amplify the power, so that it is called as a active element. Now we'll see the passive elements. I will see the passive component. Passive component is an electronic component which can only receive energy. So active component means deliver the energy. Here receive energy. It can be either dissipated or absorbed or stored in the electric field or magnetic field. So the passive component means it will receive the energy. That energy can be either dissipated or absorbed or stored in the form of either electric field or magnetic field. In previous active component that deliver the energy. Here the energy is receive the energy. Passive element do not need any form of electrical power to operate. There is no specific power is needed to operate this element. If you connect in the circuit, it will do the work. No need to go for any power to operate. Passive device do not provide gain or amplification. It will not provide any amplification. Either it will absorb the energy or dissipate the energy or store the energy. it cannot amplify, oscillate or generate an electrical signal, right? It will not do any amplification. We will see the examples one by one. First we will see the resistor. Resistor cannot deliver any energy to the circuit, but it will receive the energy and dissipate as a heat as long as the current is flowing. So no power is required to operate the resistor. Once the resistor is connected, it will absorb the energy and dissipate in the form of heat, right? So that is the done by the resistor. Similarly, inductor. This inductor can store the energy in the form of magnetic field and can deliver that energy to the circuit. During discharging, it will deliver. So inductor can store the energy in the form of magnetic field. Similarly, capacitor. The capacitor can store the energy in the form of electric field. During the charging time, it will store the energy. So the resistor will receive the energy and dissipate as a heat. Inductor will store the energy in the form of magnetic field. Capacitor will store the energy in the form of electric field. Then the transformer. So the transformer, we have step up transformer or step down transformer. It will increase the voltage or decrease the voltage. Secondary voltage may be greater than the primary voltage, or secondary voltage may be less than the primary voltage. Here the voltage is increased, but power and energy remain the same. There is no change in the power. When the voltage increases, automatically current will decrease, so the total power remain constant both in primary as well as secondary. So there is no amplification, only the voltage level changes. Accordingly, the current level also changed. While increasing the voltage in the secondary side, the current will decreases. While decreasing the voltage in secondary side, the current will increases, so that power remain constant in primary as well as secondary, right? So this resistor, inductor, capacitor, transformer are passive elements. No specific energy is needed to operate, just it will absorb or it will receive the energy. There is no amplification done by this component, that's why it is called a passive components. Now we'll compare this active and passive components one by one. Now we'll compare this active and passive component. So the active component means active device transform and inject power or energy into the circuit. It will deliver the energy or power to the circuit. But passive component utilize the power or energy into the circuit. Either it will absorb or dissipate as a heat, or store in the magnetic field, or store as a electric field. It will receive the energy, but here it is the energy is injected into the circuit. Then next point, all element produces energy in the form of voltage or current. Active elements are produce the energy in the form of voltage or current. Passive elements store the energy in the form of voltage or current, right? It will produce the energy in the form of voltage and current. Here passive element store the energy in the form of voltage or current. They have function and provide a power gain. For example, transistor is a power amplifier. So the amplification is possible, power gain is possible, but in passive component they do not have any provide power gain. Power gain is not possible in the passive component, just it will absorb the energy. It can control the flow of current. For example, amplifier, automatically it will control the flow of current, but it cannot control the flow of current. Right? Just it will absorb or store the energy. Active components require external and conditional source to operate in the circuit. Right? This amplifier other than voltage source, current source mean we need to give the supply to the voltage source, then only it will work. So the external and conditional source is required. For example, power amplifier mean we need to give the power, then only it will be amplified. So external and conditional source is required to operate this active components. But in passive components do not require any external source to operate. Just it will While connecting, it will absorb the energy what is available in the circuit, and either it is stored or it will absorb in the form of heat. Right? So the external source is not required for passive components. Now we'll see some examples. So already we discussed the diode, transistor, solar PV cell, PV panel. These are all the example for active components. That is, it is able to deliver the energy to the circuit. It is able to go for a power gain. For this, the external source is required. But while going to passive components, it will not deliver. It will receive the energy. But no specific power is needed to operate. There is no power gain also. What are the example? Antennas, capacitors, detector, inductor or coil, network, sensor, transducer, cable, crystals, PCB, switches, terminals, connectors. So these are all passive components. Just while connecting in the circuit, it will receive the energy from the circuit. It will not go for any amplification. It will receive the energy and it will do the work. Right? So in this video, we discuss about what is active component, what is passive component, what are the examples available, what are the comparison available, we discuss. Thank you. Welcome viewers. In this video, we'll see the unilateral and bilateral element. First, we'll see the unilateral element. So the unilateral circuit elements are those elements that allow the flow of current in only one direction. It will allow the current in only one direction. So when the polarity of the power supply changed or reversed, either it will oppose the flow of current or shows the different property. So it can able to, the current will flow in only one direction. Suppose if you reverse the current or reverse the polarity, it will work with the different characteristics. So that it is called a unilateral. Unilateral means only one direction. If the direction changes, its property will change. So the VA characteristics of unilateral element changed when the polarity of the applied voltage reversed. Right? It will give the different VA characteristics. It will work only one direction for a current flow with the only one direction. If any change in the current direction or polarity, the property will change. Right? So the example for this unilateral element, diode ACR. So the diode ACR, so we know that forward bias and reverse bias. If anode is positive with respect to cathode, this is forward bias. If anode is negative with respect to cathode, it will reverse bias. So during forward bias, conduction is there, but during reverse bias, there is no conduction. So while changing the polarity, the property of the diode also changes. Similarly, ACR also. The ACR also very similar thing. Only thing you have gate terminal. So the anode is positive with respect to cathode. While giving the gate signal, it will start conduct. Suppose if anode is negative with respect to cathode, it is reverse bias. Even if you give the gate signal, it will not conduct. So during positive application of voltage, it will conduct. But if you apply the negative voltage to anode, it will not conduct. So that it is called a unilateral element. So the circuit using diode and AC are called a unilateral circuit. Right? We will see the circuit diagram. So this is nothing but a bridge rectifier. So 4 diodes are available, D1, D2, D3, D4. So this is entire circuit is called a unilateral circuit. So this is the unilateral element. This diode is the unilateral element. It will conduct only in one direction, positive. During negative mean it will not conduct. Right? The AC voltage is given, we are getting the DC output. So during positive half cycle, D1 and D2 will conduct. D3 and D4 will not conduct because reverse bias. During negative half cycle, D3 and D4 will conduct, but D1 and D2 will not conduct. So it will work in only one direction. In order to get both positive and negative direction, negative cycle, we are having 4 diodes are connected. So it will work in a one direction. Now we'll see the bilateral element. Now we'll see the bilateral element. Bilateral elements allow the current to flow in both direction through them. It can be able to, the current can flow in both positive direction as well as negative direction. The VI characteristics of bilateral element do not change so much with the reversal of the applied voltage. So during positive or negative, either the current direction is positive or negative, the characteristics will not change much more. It can be able to function for both positive current as well as negative current. They are mainly three passive elements, means they are not require any external voltage to work, and all of them are bilateral in nature. Basically there are three passive elements available, that is nothing but resistor, inductor and capacitor. These three are also called as a passive element. There is no external source is required. The active and passive element, the separate video available, the link is available in the description box. You can, the viewers can see that what is meant by active and passive components. Available separate video, the link is available in the description box. So this resistor, inductor, capacitor is called a passive element that do not require any external force, external source. So during the change of current, polarity of voltage or current will not much more affect, right? It will act as it is. So the example is resistor, inductor, capacitor. So this bilateral circuit is available. It's a connected resistor. So either the current is positive or negative, it will act as a resistor. It will absorb the power. It will not bother about whether the current is positive or negative. Now we'll go for a comparison between unilateral and bilateral element. We'll go for a comparison. So we'll compare this unilateral element and bilateral elements. So in unilateral element, it allows the flow of current in one direction only one direction. But it allows the flow of current in both the directions, right? Both the direction is possible. The VI characteristics change with the reversal of applied voltage, right? We already discussed forward bias and reverse bias of the diode. If we apply positive voltage, it is forward bias diode. If we apply negative voltage, it becomes reverse bias. So the polarity will change, the characteristics also will change. But here the VI characteristics do not change with the reversal of the applied voltage. Here will not change. For example, here we have resistor, capacitor and inductor. And one more point is available. The resistance and impedance property vary so much with the varying the following current, while varying the flowing current, right? So in this case the property will change, but the resistance and impedance property do not vary so much with the varying the flowing of current, right? Why? Because diode SCR is very important. Positive voltage is applied means forward bias, negative voltage applied means reverse bias to the anode. But here, so it will vary the property, but here not like that. Either positive or negative voltage, this resistor will absorb the energy and dissipate in the form of heat. Inductor will store the energy in magnetic field. Capacitor will store the energy in electric field, right? Much more change, right? So in this video we discuss what is unilateral element, what is unilateral circuit, what is bilateral element and bilateral circuit, and comparison with example also we discussed. Thank you. Welcome viewers. In this video we will see voltage source and current source, the details of voltage source and current source. First will the source. The source is a device which converts the mechanical, chemical or thermal or some other form to electrical energy, right? So the source is nothing but any form of energy into electrical energy. That is called a source, either mechanical, chemical or thermal or some other form. So the classification is available here. The source is divided into voltage source and current source. Voltage source and current source. Voltage source further divided into ideal voltage source, practical voltage source. We will see what is meant by ideal voltage source, practical voltage source one by one. Similarly, current source is again divided into ideal current source and practical current source, right? The source, we have two types, voltage source, current source. In both voltage and current source we have ideal as well as practical. We will see this one by one. First let's go to the voltage source in that ideal voltage source. So the voltage source, the symbol is like this, either the circle or this positive and negative terminals are represented. This terminal A, terminal B, so the voltage will be VAB. This will be positive and negative. It also represented by the circle VAB. So what is ideal voltage source? An ideal voltage source is a two-terminal device whose voltage at any instant of time is constant and is independent of the current drawn from it. So the voltage is always constant. It will not vary with the current drawn from it. Either the current drawn is more or less, the voltage will be the constant in case of ideal voltage source. So the circuit representation is available here. The voltage V, the terminal A and B. So the terminal A and B, the voltage will be VAB. If you draw the graph between current or time with respect to voltage, the voltage is constant. When the current increases or decreases, similarly the time increases or decreases, the voltage remain constant. For ideal voltage source, the voltage remain constant. Now we'll go to the practical voltage source. So practical voltage source, we'll see the source having some amount of internal resistance is known as practical voltage source. So the practically the voltage source having some internal resistance. So due to this internal resistance, voltage drops will take place and cause the terminal voltage to reduce. Right? So in the ideal voltage source means there is no internal resistance, but in practical voltage source some amount of internal resistance will be there. Due to the internal resistance, the voltage will drop. So due to that, there is a reduction in the terminal voltage. Right? We'll see the diagram. So the voltage source is available. This is the internal resistance R. The current is flowing. The terminal A and B, this is voltage AB. Across this terminal, voltage AB. So the graph is drawn between current or time with respect to voltage. So in case of ideal voltage, the voltage is constant. Whether the current increases or decreases, time increases or decreases, the voltage remain constant. But in case of practical, the current gradually decreases due to the drop in the internal resistance. The voltage, some amount of voltage will be dropped in internal resistance, so that when the current or time increases, the voltage is slowly decreases. So this is the difference in voltage between ideal and practical voltage source. Due to the internal resistance, there is a drop in the voltage. Now we'll go to the current source. So this is a representation, either in a circular or in a rectangular box. We can represent the current source. This direction indicates current is flowing from B to A. If it is down, means the current is flowing from A to B. This indicates the current direction. Current direction is indicated by this arrow. We can represent either circle or in a rectangular form. So the ideal current source is a two-terminal circuit element which supplies the same current at any load resistance, independent of the voltage source terminals. Right? So the ideal means it will supply the same current for any load resistance. Whether the load resistance increases or decreases, it always supplies the same current, independent of the voltage source. Right? The circuit is represented here. So this is the current source. It is the current is flowing through the terminal AB. So the graph is drawn between voltage or time with respect to current. Whether the voltage increases or decreases, current increases or decreases, the time increases or decreases, the current remains same. The current is always constant. It will not vary with the either voltage or time. This is possible only in the ideal current sources. Now we'll see what happened in the practical current source. So in the practical current source represented with an ideal current source connected with an resistance in parallel. In case of voltage, practical voltage source, the resistor is connected in series with the source. In case of current source, the resistor is connected in parallel with the current source, right? The voltage source in series with resistor as a internal resistor, current source in parallel with the resistor as a internal resistor. So due to this, some current will be diverted here. The current is flowing from current source to the terminal A. Due to this resistor, some amount of current will be drawn by this resistor. So that net current will decreases. When the time increases or voltage increases, the net current to the terminal will decreases. So that is represented by this diagram. This graph is drawn between voltage or current with respect to voltage or time with respect to current. When the voltage increases or decreases, or current increases or decreases, the time increases or decreases, the current remains same in case of ideal. But in case of practical, what we have, internal resistance connected in parallel. So some amount will be diverted to internal resistance. So the net current will decreases. So when the time increases, the current also decreases gradually. Similarly, when voltage increases, the current decreases gradually. So this is the difference between ideal source and practical source. Due to the internal resistance, there is a drop in the current value. So in this video, we discuss about the sources. There are two types, voltage source and current source. Again, there are two types, practical and ideal. Both current and voltage source we discussed. Thank you. Welcome viewers. In this video, we'll see the electrical energy sources. What are the types available? The source which supplies the active power to the network is known as electrical source. The source, from that the active power is delivered to the network, that is called a electrical source. So the classification is available. We'll see one by one. This the energy source is divided into direct source and alternating source, that is DC, direct current, and alternating current, AC. By using the sinusoidal function AC voltage, it's called a alternating source. This is using the DC. In that, again, two types available, independent voltage and current source, dependent voltage and current source. Independent means it is independent of the load. We will see these details one by one. Similarly, dependent. In this dependent, again, there are four types available. Voltage controlled voltage source. So this is the voltage source, but it is controlled by the voltage. Voltage controlled current source. That's a current source, but it is controlled by voltage. Current controlled voltage source. So voltage source that is controlled by the current. Current controlled current source. So this is the current source, but that is controlled by the current. So there are four types available. Voltage controlled voltage source, voltage controlled current source, current controlled voltage source, current controlled current source. Now we'll see this one by one. So the energy source we already discussed, it is having direct and alternating source. Two types available, direct source and alternating source. The direct source means this type of source, that is voltage and current, is not changing by any variation in the connected network. DC mean always is constant, but AC mean it is depends upon the frequency. This magnitude and direction changes continuously, but in case of the direct source, the DC means always the voltage will be constant with respect to the time, so that it is there is no change, it's not changed by any variation in the connected network. In that, again, two types, independent voltage and current source. What is independent voltage and current source? Independent sources are that which do not depend on any other quantity in the circuit, right? The voltage source or current source always give either voltage or current. It will not change by changing any other property of the quantity of the circuit. Either load voltage or some other voltage changes, the supply voltage or supply current will not change, independent. That is, the strength of voltage or current is not changed by the variation in the connected network. It always gives the constant voltage or constant current. It will not affect by affecting some other parameter. That's why it is called a independent. Always gives the constant voltage or constant current. Now we'll go to the dependent voltage and voltage source and current source. What is that? The source whose output voltage or current is not fixed but depends on the voltage and current of another part of the circuit. Right? So due to the load or some other parameter, any changes that will reflect in the source also. The source voltage and current also will be affected. The source voltage and current is not constant. It will vary along with the variation of any other part of the circuit. In any other part of the circuit, if any variation is there, then source current and voltage also changes. The strength of voltage or current changes in the source for any change in the connected network. So the previous case it is not changed, but here due to the second type dependent means any change in the network will change the voltage and current of the current source also. So it is represented by the diamond shape. All other represented by the circle. Independent source means represented by circle, dependent source represented by diamond shape. Right? So this dependent voltage source again classified into 4 types. We will see these types one by one. So first we will see the voltage controlled voltage source. See the diagram. So this is the voltage source, terminal AB. So due to dependent, it is represented by the diamond shape. The terminal AB, the voltage is VAB. The another part we have one resistor is available. The terminal is CD. The voltage is VCD. So this is voltage controlled voltage source. So this voltage will control the supply voltage. That is, this VAB is proportional to VCD. VAB equal to proportional to VCD. Voltage controlled voltage source. If any changes in the VCD, this part, that will change the supply voltage also. So VAB equal to, while equating, we need to introduce one constant, K into VCD. This is a constant. So this is called a voltage controlled voltage source. This voltage will control the voltage source. Either it will increase or decrease. So in the above circuit, the voltage across the terminal AB is dependent upon the voltage across the terminal VCD. The VCD will control the voltage of VAB. Then the next type, voltage controlled current source. So this is a current source that is controlled by voltage. See, this is a current source. AB, terminal AB, the current flow is IAB. Another part what we have, one resistor is available, CD. The voltage is VCD. In voltage controlled current source, the current of the source IAB depends upon the voltage across the terminal CD, that is VCD. Right? So that it is called a voltage controlled current source. So the current IAB is proportional to VCD. The VCD will change the flow of current. While equating, we need to introduce one constant, that is this symbol IAB equal to VCD. This symbol is nothing but a transconductance, because it is I by V. V by I is resistance, I by V is transconductance. The unit is mho. In case of resistance, it is the ohm. Here mho. So this is nothing but a voltage controlled current source. Any change in the voltage will change the flow of current in the current source. Now we'll go to the next type. So this one, current controlled voltage source. So this is a voltage source. This is a voltage source is available. It is controlled by current. Current controlled voltage source. In the current controlled voltage source, the voltage source of the network depends upon the current and the current of the another network. So this is diagram. So we have voltage source is available, VAB. Here one resistor available, that terminal is CD. So the current is ICD. So this current will control this voltage. So that it is called a current controlled voltage source. VAB is directly proportional to ICD. This current will control the voltage. So VAB equal to R into ICD. R is the constant. Now we'll go to the next type. Current controlled current source. So this is also current source controlled by the current. Current controlled current source. So the current controlled current source means the current source is depend upon the current of the another branch. So this is one current source is available. This current source is depends upon the current flowing in the resistor. This terminal is AB, IAB. This terminal is CD, ICD. So this ICD will change the performance of IAB. So IAB is directly proportional to ICD. So IAB equal to beta into ICD. Beta is the constant. So current controlled current source. So in this video we discuss about the energy source. Basically two type: direct source, alternating source. Then dependent, independent voltage and current source. In dependent again four types: voltage controlled voltage source, voltage controlled current source, current controlled current source, current controlled voltage source. There are four types. These types are we discussed. Thank you. Welcome viewers. In this video we will see the Ohm's law, definition, limitations and problems. First we will see the Ohm's law. The Ohm's law states that current flowing through the electric circuit is proportional to the potential difference across the circuit and inversely proportional to the resistance of the circuit, then provided temperature remain constant. So what is the statement given? The current flowing through the circuit is directly proportional to potential difference across the circuit and inversely proportional to resistance of the circuit. I is directly proportional to V by R. Directly proportional to potential, inversely proportional to resistance. So by cross multiplying this we can write V equal to IR. That is a very basic formula in electrical. Voltage equal to current into resistance. Based on the Ohm's law, what we got? V equal to I into R. The important thing is the temperature remain constant. Because when the temperature changes, the resistivity, current, everything will change. So based on the condition temperature remain constant, then only this I equal to V by R, so that V equal to I into R. So temperature remain constant. Now we'll see the power expression for power from this Ohm's law. V equal to IR. The power is nothing but V into I, voltage into current. V into I, the power, we know that power equal to voltage into current. But based on the Ohm's law, what is V equal to IR? We will substitute this V equal to IR. So that power equal to IR into I. This V is replaced by IR. Then this I is written. So what will happen? I square R. So power can be expressed in a new formula is called I square R. The general formula is V into I. The V is substituted with IR. So that what we got? I square R. So the power in terms of current is nothing but I square R. Generally it is called as a power loss. Because the loss is depends upon the current, so this term is normally referred as a power loss. And one more expression, power equal to V into I, but based on the Ohm's law, V equal to IR, I equal to V by R. Now we will substitute I equal to V by R. Previously we substituted V equal to IR. V is replaced. Now we will replace I. So I equal to V by R. So that power equal to V into I is nothing but V by R. So that V square by R. So another formula for power is in terms of voltage is V square by R. So we got two different expression for power. So this is a general expression, voltage into current. This expression based on current and resistance, I square R. This expression based on voltage and resistance, V square by R. So 3 different formula available based on our requirement, based on the data. We can use either any of this formula. Now we'll go to the limitations. What are the limitations of Ohm's law? The Ohm's law does not apply to all metallic, non-metallic conductors. So it is applicable only metallic conductors. Non-metallic conductors is not applicable. We cannot apply the Ohm's law to non-metallic conductors. It also does not apply to non-linear devices. Only applicable for linear devices. Linear devices mean when current increases, voltage also increases linearly. But in non-linear devices, we cannot apply the Ohm's law. The example is Zener diode. We cannot apply Zener diode. For non-linear devices, we cannot apply the Ohm's law. The third one, Ohm's law is true for metal conductors at constant temperature. We already discussed, if temperature changes, a voltage, current, everything property will change. So we cannot apply the Ohm's law. Only when the temperature is constant, then only we can apply the Ohm's law. If temperature changes, the law is not applicable. We cannot apply the Ohm's law. Right? So it is applicable only metal conductors under the constant temperature. Non-metal conductor is not possible. Non-linear device also not possible. So these are all the limitations of the Ohm's law. Now we'll see the resistance, resistivity. One more term is available, resistivity. We'll see now. We'll see this resistance. What are the property of the resistance? Resistance of a metallic conductor depends upon the following. The resistance of any metallic conductor having this following properties. One is directly proportional to length of the conductor. The resistance is directly proportional to length of the conductor. If length increases, the resistance also increases. It is inversely proportional to cross-sectional area of the conductor. The cross-sectional area, it is inversely proportional. When the cross-sectional area increases, resistance will decrease. And this depends upon the nature of the conductor. It depends upon the nature of the material of the conductor. Depends upon the material, the own property of the material. And it is depends upon the temperature of the conductor that we already discussed. Resistance is Ohm's law is applicable only constant temperature. So it is depends upon temperature also. So based on the above statement, it is clear that R is directly proportional to L by A. Directly proportional to length of the conductor, inversely proportional to area of the conductor. So while equating, we are introducing one constant called rho. Rho is nothing but resistivity. That is depends upon the nature of the material of the conductor. It is given by the manufacturer. Resistivity. One more term is called a resistivity. So that R equal to rho L by A. So we can find the resistance based on these three parameters. Resistivity, length of the conductor, area of the conductor. So this resistivity depends upon the material, nature of the material. So similar to resistivity, we have conductance. Resistance like that, the inverse one is the conductance. Resistance means opposing the flow of current. Conductance means it is allow the current to flow in the conductor. So the conductance G, the term is G. Conductance is the inducement to the flow of current. Hence conductance is the reciprocal of resistance. Resistance will oppose the flow of current, but conductance will inducement to the flow of current. So both are inversely proportional, reciprocal. Both are reciprocal. So G equal to 1 by R. Resistance, this is conductance. So now we discuss the resistance in terms of resistivity and conductance. Now we'll go for a problem. We'll solve 3 different problems. We'll see the first problem, problem 1. The resistance of a conductor 1 millimeter square in cross-sectional area and 20 meter long is 0.346 ohm. The resistance of the conductor is given 0.346. The area of cross section is 1 millimeter square. Then length is 20 meter. Determine the specific resistance of a conducting material, that is resistivity. We need to find the resistivity, right? The resistance cross sectional area length is given, we need to find the resistivity. So first we'll convert the given data into meter. So area equal to 1 millimeter square. In order to convert into meter square, 10 to the power minus 3. Meter to millimeter to meter mean 10 to the power minus 3. Here meter square is there, millimeter square. So 10 to the power minus 6 meter square. So 1 into 10 to the power minus 6. So the millimeter square is converted into meter square. The length is 20 meter. Is already given in meter. The resistance is 0.346 ohm. These three data are available. So what we need to find? The resistivity. How will you find the resistivity? The formula available. R equal to rho L by A. Just now we discussed. R equal to rho L by A. So cross multiply this. R into A equal to rho L. Bring the L in the denominator. R A by L equal to rho. That is rho equal to R A by L. So from this formula, all these values are known. So we can find the rho. So it is rearranged in such a way that rho equal to R A by L. Now we can substitute the value of this R, A and L. R is 0.346. A is 1 into 10 to the power minus 6. The length is 20 meter. So by simplifying, what we got? 0.0173 into 10 to the power minus 6 ohm meter. The unit for resistivity is ohm meter. 0.0173 into 10 to the power minus 6. So we will move the decimal into two places. So that 1.73 into 10 to the power minus 8 ohm meter. Right? The decimal is moved to two places. So that this 10 to the power minus 6 become minus 8. This value increases mean power also increases. 1.73 into 10 to the power minus 8 ohm meter. Right? So this very simple problem. In this formula, R is available, L is available, A is available. So that easily we can find the rho, resistivity. Right? Now we'll go to the second problem. The second problem is the electric heater draws 80 ampere from 250 voltage supply. One electric heater is there, it will take the 8 amperes from the supply 250 voltage. What is the power rating? And also find the resistance of the heater element. Two questions we need to find. What is the power rating and what is the resistance of the heating element? So the given data, the current is drawn by is 8 ampere. Supply voltage 250 amperes. So these two data are available. Supply voltage and the current. What is the power rating? Power rating is nothing but V into I. Voltage into current. Voltage is 250, current is 8 ampere, so 2000 watts. The power rating of the heater is 2000 watts. V into I. What is the resistance R? R equal to V by I. Based on Ohm's law, V equal to IR. So R equal to V by I. V is 250. I is 8, so 250 by 8, 31.25 ohm is 31.2. The resistance of the heater element is 31.25 ohm. Right? So we calculated power rating as well as resistance of the heater element. Now we'll go to the next problem. We'll refer the third problem. What will be the current drawn by the lamp rated 250 voltage 40 watts connected to 230 volt supply? Right? So the one lamp is available. The rating of the lamp is 250 watts 250 volt 40 watts. We need to find what is the current taken by this lamp. It is connected across 230 volt. Since this 250 is the rating, this 230 is the supply voltage. It is connected across 230 voltage. Right? So what are the data available? Rated power is 40 watts. rated voltage is 250 watts. Supply voltage is 230 watts, 230 volt. Now we'll find the, what is the question? We need to find what is the current taken by the lamp. In order to find the current, first we will find the resistance R. R equal to V square by P, because the power is available. What is the formula relating power and resistance? Just now be discussed. V equal to power equal to V into I, one formula. I square R, another formula. V square by R, another formula. So here V and P is available, so that we can use this formula. P equal to V square by R, from that R equal to V square by P. So V is 250 square divided by power rating 40, so that 1562.5 ohm. Right? From the given data, power and voltage, we calculated the resistance of the lamp is 1562.5 ohm. Right? So the power P equal to V square by R, from that R equal to V square by P. So now we got the value of current, resistance. Already supply voltage is available. So from this R and V, we can easily calculate the current. Current I equal to V by R. V is already given, supply voltage 230. 250 is the rated voltage, but supply voltage only 250. Resistance now, just now we calculated 1562.5 ohm. So we can substitute here. V equal to 230, R equal to 1562.5, so that 0.1472 amperes. So the current drawn by the lamp is 0.1472 ampere. Right? So in this problem, power and voltage is given. From that we calculated the resistance. From the resistance we calculated the current drawn by the lamp. Now we'll go to the next problem. So the fourth problem is, a battery has an EMF of 12.8 voltage and supply a current of 3.24 ampere. One battery is available. The EMF of the battery is 12.8 voltage and current is 3.24 amperes. What is the resistance of the circuit? We need to find what is the resistance. How many coulomb leaves the battery in 5 minutes? How many coulombs leaves the battery in 5 minutes? The two questions we need to find. Right? So what are the data available? The battery EMF is given, V equal to 12.8 voltage, and current is given 3.24 ampere. 3.24 ampere, the current is given, and time also given, 5 minutes. 5 minutes means 5 into 60 seconds. Converting into 6 seconds, we need to multiply 60. So the resistance can be easily calculated. R equal to V by I. The formula is there, R equal to V by I. That is V equal to IR. From that R equal to V by I. Both are given. Voltage EMF is given 12.8. Current is given 3.24 ohm. So this 12.8 by 3.24, what we got? 4 ohm. The resistance of the circuit is 4 ohm. And what is the charge leaving the battery? Charge is nothing but current into time in seconds. Current is 3.24. Time is 5 seconds, 5 minutes. 5 into 60 is a second, converted into seconds. So 5 into 60. 972 coulomb. So the charge leaving the battery in 5 minutes is 972 coulomb. Right? So in this problem, voltage, current and time is given. From that we calculated the resistance, voltage by current, and we calculated the charge using the formula current into time. Right? That is 4 ohm. This is 972 coulomb. So in this video we discuss about the Ohm's law, what is the definition and what is the formula. Then power in terms of resistance, V square R, I square by R, 2 times. Then limitations of Ohm's law. Then resistance. What are the property of the resistance? In this the important thing, resistivity. We discuss about the resistivity. The resistance mean the reciprocal conductance, that also we discussed, and we discuss the 4 problem based on this Ohm's law. Thank you. Welcome viewers. In this video we will see the combination of resistor. The resistors can be connected in 2 different ways, either series or parallel. So we will see this one by one. First we will see the series combination. Series combination means the resistors are connected end to end. One end of the resistor connected to another end of the resistor, so that it is called a series combination. You can refer the diagram here. R1, R2, R3. 3 resistors are connected in series. One end of the resistor connected to another resistor, thereby another resistor. R1, R2, R3. This is called a series combination. It is given with a supply voltage V. The current flowing is I. This terminal is A, this terminal will be B. The important thing in this series combination is the same current is flowing through all 3 resistors. Current is same. Only one current I is flowing through R1, R2 and R3. Because of series combination, series connected, only the current I is flowing through all the resistors. This is the one important point. This V1 is the voltage drop across R1. V2 is the voltage drop across R2. V3 is voltage drop across R3. So the V is the applied voltage. This voltage will be dropped across R1, R2 and R3, depends upon the R value. So depends upon the R value, the voltage will be dropped. So this V1, V2, V3, sum of these 3 is nothing but total voltage. Total voltage V equal to V1 plus V2 plus V3, because this V only dropped across these 3 resistors. So V equal to V1, V2, V3. So the 2 important thing, one is current is equal in all the resistors. Second one, the voltage, applied voltage V equal to sum of V1, V2 and V3. That is V equal to V1 plus V2 plus V3. So these 2 are important points in this series combination. So these 3 resistors can be converted into single resistor, equivalent resistance, total resistance between the terminal A and B. Now we will see what is the total resistance in case of seriously connected. We will see the expression. How will you find the total resistance? So in this is given, the description is given, since there is only one closed loop, only one current is flowing. The first one. In other words, if the current is same through all the resistor, this combination is called a series combination. The series combination is easily identified. If the current is same in all the resistor, means the same current is flowing, means that resistors are connected in series combination. Now V is the applied voltage, I is the series current. V1, V2, V3 is nothing but voltage drop across resistor R1, R2, R3. First we will find what is the voltage across V1. V1 is nothing but I into R1. V equal to IR. V1 equal to I into R1. Voltage drop across the resistor R1, so that it is I into R1. Voltage drop across R2 is V2 equal to I R2. Similarly V3 is I R3. The current is same in all the cases, only the resistor and voltage will be different. The current is same. We already discussed the total voltage equal to V1 plus V2 plus V3. Voltage drop across R1, R2 and R3. That is the important thing in the series combination that we already discussed. The current is equal, potential is different, the sum of all potential is equal to total potential. Now we'll substitute this value. V1 is nothing but IR1, V2 is IR2, V3 is IR3. The current is same. So we'll take the current outside. V equal to I into the I is taken outside, so that R1 plus R2 plus R3. So this R1 plus R2 plus R3 is nothing but a total resistance, RT. RT is nothing but R1 plus R2 plus R3. So in the series combination, the total resistance is nothing but sum of individual resistance. So the series combination means very simple. We need to add all the individual resistance. That will give the total resistance. So that is given. The total resistance is equal to the sum of the individual resistors. We need to add all the resistors, right? So in this series combination, first important point is the current is equal. Same amount of current is flowing. Potential drop across each resistor, sum of potential drop across each resistor is total potential. V equal to V1 plus V2 plus V3. So by analyzing, we found that the total resistance equal to sum of individual resistance for series combination. Now we'll go to the parallel combination. Now we'll go to the parallel combination. What is parallel combination? If one end of all the resistor is joined to a common point and other ends are joined to the another common point, then the combination is said to be parallel combination between the two common points. The one end of all the resistors are connected in one common point, another end is connected to another common point, then that combination is said to be parallel. Now I will refer this diagram so that it is easier. See that the three resistors available, R1, R2, R3. This one end of all the resistors are connected together. This is common point A. Another end also connected together. Another end of all the three resistors are connected together. This is point B. So this is common point, another common point. Right? In series resistor means it is connected end to end, but parallel combination it is connected, one ends are connected together, another ends are connected together. This end is A, this end is B. It is supplied with the supply voltage V. Supply voltage V is given. This is the current, total current I is flowing through the resistor. I is flowing through the circuit. So the current I is flowing. At this point what will happen? The current will be divided because three different paths available. So the current will be divided. I1, I2, I3. Current is divided. In case of series combination, the voltage is divided. Now the current is splitted. Current flowing through R1 is I1, R2 is I2, R3 is I3. So total current I equal to I1 plus I2 plus I3. So there is an important thing in this parallel combination. In series combination, V equal to V1 plus V2 plus V3. But here the current is, total current equal to sum of current flowing through each resistor. What about the voltage? The same voltage is applied across R1, R2 and R3. The voltage what we applied V is available across R3, R2 as well as R1. The voltage will be same. The current will be different. So this parallel combination can be converted into single resistor, total resistor or equivalent resistor between A and B with a supply voltage V. We will see what is the resistance R. How will you find what is the expression for total resistance in case of parallel combination? We will see now. So V is the applied voltage. I1 and I2, I3 is the current flowing through R1, R2 and R3. So by Ohm's law we will find the I value. I equal to I1 equal to V by R1. I already told V is same across all the resistor. Only the current will be different. So I1 is the current flowing through resistor R1. So I1 equal to V by R1. Similarly I2 equal to V by R2. I3 equal to V by R3. And another important thing, total current equal to sum of this current flowing through the resistors. Previous in the series combination, V equal to V1 plus V2 plus V3. Here I equal to I1 plus I2 plus I3. Now substitute the value. V by R1 plus V by R2 plus V by R3. The voltage is common, so we can take the voltage outside. So what we have? I equal to V into 1 by R1 plus 1 by R2 plus 1 by R3. So this is nothing but the total resistance 1 by RT. So Vi equal to V into 1 by RT. So that we can write I equal to V by RT. So what is this RT is nothing but 1 by R1 plus 1 by R2 plus 1 by R3. Now we'll see the further simplification. So 1 by RT equal to 1 by R1 plus 1 by R2 plus 1 by R3. So now we'll go for a simplification. We'll take the LCM. 1 by RT equal to, so the R1, R2, R3, 3 terms available. So we will take the LCM as R1, R2, R3, all 3. So here R1 is available, R2 and R3 is not available. So it is R2 plus R3. Here R2 is available in the common LCM. So R1 and R3 is multiplied here. Plus here R3 is available. So R1 and R2 is multiplied. So it is R2 R3 plus R1 R3 plus R1 R2 divided by R1 R2 R3. So this is 1 by RT. What about RT total resistance? It is inverse. Just you have to change the numerator and denominator. So R1 R2 R3 divided by R1 R2 R3 plus R3 R1. So this is the total resistance in case of the parallel combination. The 3 resistors. Suppose the 2 resistors are available. What is the total resistance? 2 resistors are available. 1 by RT equal to 1 by R1 plus 1 by R2. Only 2 resistors. Normally we will refer the 2 resistors. This formula only we are frequently using. So 1 by RT equal to, take the LCM, R1 R2, 2 terms available. Here R1 is there, so we need to multiply with R2. Here R2 is there, so we need to multiply with R1. So this is 1 by RT. What is RT? Just you have to interchange numerator and denominator, reciprocal. You have to take the reciprocal. So R1 R2 divided by R1 plus R2. So this is a standard formula. In case of parallel combination, the resultant or equivalent or total resistance is R1 R2 divided by R1 plus R2. Multiply both the resistor divided by sum of both the resistors. R1 R2 divided by R1 plus R2. So now we got the expression for total resistance in case of parallel combination for 3 resistor as well as 2 resistor. Now we'll see one problem. So in this problem we need to calculate the equivalent resistance of the following combination of resistor and also source current. So one circuit diagram is given. In this we need to find what is the total resistance and also what is the total current, source current. So here 12 ohm resistor available, 16 ohm and 4 ohm. There is another 6 ohm available and 40 ohm available. Now we need to simplify this resistor by using this series parallel combination. By using series parallel combination we can simplify this circuit. So in this circuit, it is, by seeing this, it is clear these two are connected in parallel. By seeing the diagram, it is very clear that 12 ohm and 6 ohm are connected in parallel. There is no overlap here. Suppose we cannot take this because this is connected, another 40 ohm, here 6 ohm is there. Here there is no overlap. This 12 ohm and 6 ohm are connected in parallel. Now we'll change this. Now we'll find the equivalent resistance for this 12 ohm and 16 ohm. Right. So that diagram is available here. See this. This 12 ohm and 6 ohm are connected in parallel. We'll take this is R1 and this is R2. What is the total resistance in case of 2 resistors connected in parallel? R1 into R2 divided by R1 plus R2. So that is equal to 12 into 6 divided by 12 plus 6. That is 72 divided by 18. It is 4 ohm. So the combination of these two resistors are parallel, right? While simplifying this, what we got is a 4 ohm. These two resistors connected in parallel, by finding the total resistance, it is 4 ohm. So this parallel combination can be replaced with a single resistor of 4 ohm, this 4 ohm, right? This 4 ohm is replaced, right? So the 12 ohm and 6 ohm resistors connected in parallel, that equivalent resistance we calculated 4 ohm, so that it is replaced with 4 ohm. Now by seeing this diagram, it is very clear, this 4 ohm and 16 ohm are connected in series. There is no overlap. Easily we can identify these two are in series, right? Now we'll go for the further simplification. See this 4 ohm and 16 ohm. This 4 ohm and 16. We'll take this R1 and R2. So if the resistors are connected in series, what is the total resistance? R1 plus R2. We need to add both the resistor. 4 ohm plus 16 ohm. That is 20 ohm. Right? So the 4 ohm and 60 ohm are connected in series, mean the total resistance is 4 plus 16, 20 ohm. So this combination now replaced with a single resistor 20 ohm. We have one more resistor available, 40 ohm. So that is connected between 16 and 4 ohm. So by seeing this diagram, it is very clear. This 20 ohm and 40 ohm are connected in parallel. There is no overlap. These two are connected in parallel now. Now we can replace this with a single resistor. I will go for this further. See, this 20 ohm and 40 ohm are connected in parallel. What is the formula? RT equal to R1 R2 divided by R1 plus R2. For simplification, we are taking this R1 and R2. Right? This is not, there is no standard. This for this combination, we are taking 20 ohm as R1, 40 ohm as R2. So 20 into 40 divided by 20 plus 40. So that is equal to 800 divided by 60, that is equal to 13.33 ohm. 13.33 ohm. The combination, parallel combination of this 20 ohm and 40 ohm, the equivalent resistance is 13.33 ohm. So this 2040, this combination can be replaced with this 13.33 ohm. This is replaced. That parallel combination is replaced with 13.33 ohm. Here another 4 ohm is available. So by seeing this diagram, it is clear these two are connected in series. The equivalent resistance is sum of these two. 13.33 plus 4 is nothing but 17.33. Right? Now we'll see this diagram. So this 17.33 ohm. Then supply voltage is 50 volt and the current is I. Now it is converted into only single resistor. Right? The every series and parallel combination resistors are combined resistors are identified, and finally we got only one resistor. So from this diagram we can easily identify what is the current. Right? So the total resistance is nothing but 17.33 ohm. One question is total resistance. So we calculated total resistance equal to 17.33 ohm. Then what is the current? I equal to V by R. V is available and R also available. V is 50 volt and R is 17.33 ohm. So we can find the total current or source current, that is equal to V by R. V is 50, R is 17.33. So that after simplification we got 2.88 ampere. So the total current or source current is 2.88 ampere. So in this problem, there are series and parallel connector resistors are there. That is simplified and equivalent resistance is calculated. Finally, we got only one resistor, total resistance of 13.33 ohm. From that, we calculated total current or source current also. So in this video, we discuss about the series combination of resistor. What is the equivalent formula? Parallel combination of resistor. What is the equivalent formula? Based on that, we solved one problem. Thank you. Welcome viewers. In this video, we'll see the problem related to the series and parallel combination of resistor. The detailed explanation of series and parallel combination of resistor, the derivation and explanation available in previous video. The link is available in the description box. You can see the detailed explanation of the series and parallel combination. This video related to the problem based on series and parallel combination of resistor. First we will see the formula. The series combination. If the resistors are connected in series, mean the resultant resistance will be R1 plus R2 plus R3. If three resistors are connected in series, mean the resultant resistance is total resistance is nothing but sum of individual resistance. You have to add all the resistors R1 plus R2 plus R3. In case of parallel combination, if three resistors are connected in parallel, the resultant value will be R1 R2 R3 divided by R1 R2 plus R2 R3 plus R3 R1. Suppose the two resistors are connected, mean R1 R2 divided by R1 plus R2. So based on this formula, we'll go for the problem. The detailed explanation available in previous video, you can see that the link is available in the description box. Now we'll go to the problem 1. So the circuit is available. In this circuit diagram, we need to find the equivalent resistance and current flowing through a source of 12 voltage for the circuit shown below. So for this circuit diagram, the combination of resistors available, we need to find what is the total resistance, equivalent resistance, as well as what is the current flowing through this the source 12 voltage. Now we'll see this. How will you find the series and parallel resistor? If the current flow, the same current is flowing through the resistor, that resistors are connected in series. If the current is diverted at this point, that means that two resistors are connected in parallel. So based on the current value, we can easily identify whether it is connected in series or whether it is connected in parallel, right? If the same current flowing means series, if the current is diverted means parallel, right? So we start from here. We'll say that the current is I1. The current flowing through the source 12 volt source is I1. So the I1 is flowing through 25 ohm. So at this point, what will happen? The current will divert. Because of branch, it is diverted. I2, I3. What is the meaning? These two resistors are connected in parallel, right? This 100 ohm and 50 ohm are connected in parallel. Again, this I2 is flowing through 100 ohm. At this point, again the current is diverted. This I5, I4. What is the meaning? This I4, I5. So this 5 ohm and 10 ohm, these two are connected in parallel, right? So these two are connected in parallel. These two are also connected in parallel. So by seeing the current flow, we can easily identify. So the I1 is flowing through 25 ohm, that is divided into I2 and I3 through 100 ohm and 50 ohm. Again that is divided into I4 and I5 through 5 ohm and 10 ohm. So these two are parallel and these two are parallel. Now how will you simplify this? So in this circuit diagram, this type of circuit diagram, we have to follow from the load end opposite to the source. We cannot simplify from this source end. We can follow from this opposite to the source end. Normally it may be taken as a load end. From load to source we need to follow. We cannot simplify from source to the load. We need to follow from this side to source, right? We need to follow from this end. So first we will follow this end. That is, these two are connected in parallel. We will go from right hand side to left hand side. Right, so by seeing this diagram, it is clear these two are connected in parallel. So if these two are connected in parallel, we can find the equivalent resistance. So that calculation available here. So this 5 ohm and 10 ohm are connected in parallel. This 5 ohm and 10 ohm. We'll take this is R1 and R2. For simplification purpose, we assume that 5 ohm is R1, 10 ohm is R2. What is the total resistance? R1 R2 divided by R1 plus R2. So this is the formula for when two resistors are connected in parallel. So what is that? 5 into 10 divided by 5 plus 10. That is 50 divided by 15, 3.33 ohm. resultant will be 3.33 ohm. So these two resistors are connected in parallel. By inspecting the current, we easily identify these two are in parallel. So the equivalent resistance of these two parallel resistor is 3.33 ohm, right? Now we can replace these two with 3.33 ohm, right? That is available in the next diagram. See this, right? That parallel combination now converted into 3.331. What we calculated is replaced. Now from this diagram it is clear that these two are in series. See, the same current is flowing through 100 ohm as well as 3.33 ohm. The same current is flowing. What is the meaning? These two are connected in series. If series mean R1 plus R2. We will take 100 as R1, 3.33 as R2. So the resultant, if it is connected in series, R1 plus R2, 100 plus 3.33 ohm, that is 103.33 ohm. These two are in series. The equivalent resistance will be 103.33 ohm. Now we'll replace this with this value. So after replacing, what we got? 103.33 ohm. So these two are other two resistors available. So from this diagram, it is easily we are able to understand these two are in parallel because the current is diverted here. Current flowing through 25 ohm is diverted here. So these two are in parallel. Now if we take this 103.33 as R1, 50 ohm is R1 and 103.33 as R2. Now we'll find the equivalent resistance. What is the equivalent if it is connected in parallel? R1 R2 divided by R1 plus R2. 50 into 103.33 divided by 50 plus 103.33. So that is 5166.5 divided by 153.33. So that is nothing but 33.69. These two resistors connected in parallel, the equivalent resistance will be 33.69 ohm. So now we can replace these two parallel resistor with single resistor 33.69. So that is replaced here. 33.69. Now from this diagram it is clear these two are in series. The same current is flowing through 25 as well as this 33.69 ohm. So what is the resultant sum of these two, R1 plus R2? We'll take this 25 ohm as R1, 33.69 as R2. So 25 plus 33.69 is 58.69 ohm. So these two parallel combination can be replaced with a single resistor 58.69, right? So for the simplified diagram is available here. See this, now it is replaced with 58.69. So this is the total resistor. Step by step we find the equivalent resistance by using series and parallel combination. Finally what we got? 58.69 ohm. So that is nothing but the total resistance. One more question we need to find total current or source current. I equal to V by RT. V, applied voltage divided by total resistance. So 12 divided by 58.69. The supply voltage is 12 and the resistor is 58.69. So it is 0.204 amperes. So the current is 0.204 amperes. So in this problem, by solving the problem step by step using a series parallel combination, finally we got the answer. The equivalent resistance of the circuit is 58.69 and the source current or total current is 0.204 amperes. Now we'll go to the next problem. So in the second problem, we need to find the total power dissipated in the circuit zone is 18 watts. The total power in the entire circuit is 18 watts. Find the value of resistance and current in the circuit, right? So in this diagram, the 12 voltage is applied to these two resistors, the set of resistor. These two resistors are, we can easily see the parallel. These two resistors are another parallel combination. This 8 ohm, this resistor value is not known. Another parallel combination 4 ohm and 16 ohm. Right? So the total voltage is available, 3 resistors values available and 1 resistor value not available. So we need to find what is this resistor value and also what is the current. One more value what we have, the total power dissipated in the entire circuit is 18 watts. We have one more data, what is available as total power is available. So by using the total power and other terms, we need to find what is this total resistance and what is the total current. Now we'll follow with the total power. What is the total power formula? V square by R. Total power equal to V is two formula available. I square R or V square by R. Right? Here we can use V square by R because the total power is available, voltage is available. So easily we can find the total resistance. I square R we cannot follow because I square means the current value is not available. So the total power is 18, voltage applied is 12 square divided by RT, total resistance. You cross multiply, interchange these two values. So RT equal to 12 square by 18, that is 144 by 18, that is RT equal to 8 ohm. So now we got the total resistance of the circuit is 8 ohm. From the total resistance we can easily calculate the total current. I equal to V by RT. V is available 12 voltage. RT is 8 ohm. So it is 1.5 amperes. Right. So we got the total power by using the formula. We got total resistance. From the total resistance we calculated the total current 1.5 ampere. So the one question is identified. Another question, we need to find the R value. The R value is not available. This is the total resistance. One resistor value is not known. We need to find the total resistance. I will go for that. So from the diagram it is clear 8 ohm and R are connected in parallel, that we already discussed. 4 ohm and 16 ohm are connected in parallel and these two are connected in series. Two parallel combination that is connected in series. So what is the total resistance? This is first parallel combination, 8 R1 R2 divided by R1 plus R2, 8 into R divided by 8 plus R. Similarly another parallel combination, R1 R2 divided by R1 plus R2, 4 into 16 divided by 4 plus 16. Right? So this R value is not known, but this RT is we calculated. RT is 8 ohm, right? This 8 ohm is calculated, RT value is available. So in this equation only this parameter is not known, other things are available. So you can easily find the value of R. Right? Now we'll go for the simplification. Now substitute this RT equal to 8 ohm. So 8 equal to 8R divided by 8 plus R, that is 64 divided by 20. Now go for further simplification. 8 equal to 8R divided by 8 plus R plus 64 divided by 20 is 3.2. Now bring this 3.2 in the left hand side. So 8 minus 3.2. This plus 3.2 become minus 3.2 equal to 8R divided by 8 plus R. So 8 minus 3.2 is 4.8. That is equal to 8R divided by 8 plus R. Now we'll go for the further simplification. Now cross multiply this. Cross multiply so that 4.8 into 8 plus R equal to 8R. Now multiply this 4.8 into 8 plus 4.8 into R, that is equal to 8R. So 4 into 8 is 38.4 plus 4.8 R equal to 8R. 38.4, bring this 4.8 in the right hand side so that 8R minus 4.8R, while going this side it will become minus. So that 38.4 equal to this 8 minus 4.8 is 3.2R. So 3.2R can be 38.4. It is interchanged. For simplification, 3.2R equal to 38.4. Both are interchanged. So R equal to 38.4. Bring this 3.2 in the denominator. 38.4 divided by 3.2. So R equal to 12 ohm. Right? So from series parallel combination, we calculated the total, the resistance, unknown resistance is 12 ohm. So in this problem, from the given total power, we calculated total resistance of the circuit, then total current. From the combination of resistor, we already know the total resistance, so that the unknown resistance R value is calculated. Now we'll go to the next problem. So in the third problem, there are three resistors available: 30 ohm, 25 ohm and 40 ohm. You can easily see that these are connected in series. The applied voltage is 200 voltage. So we'll take this is R1, 30 ohm is R1, 25 ohm is R2, 45 ohm is R3. The voltage drop across this 30 ohm is V1. Voltage drop across 25 ohm is V2. Voltage drop across 45 ohm is V3. Right? What is the question? Total resistance. We need to find what is the total resistance. What is the total current? What is the potential difference across each element, each resistance? Right? Total resistance, total current and potential drop across each element, that is V1, V2, V3. How will you find the total resistance? It is easy. If it is connected in series, the total resistance equal to sum of individual resistance. RT equal to R1 plus R2 plus R3. 30 plus 25 plus 45, that is equal to 100 ohm. Right. Then what is the total current? I equal to V by R. V is 200 voltage. R is now what we calculated is 100. So 200 by 100 equal to 2 amperes. So we have easily calculated total resistance, that is sum of individual resistor. From RT value, by using V by RT, we calculated total current also. Now we'll go to the potential drop across each element. That is also very easy. V1 equal to I into R1, because current is same in entire series circuit. So the current will be I. Potential drop across R1 is V1, R2 is V2, R3 is V3. So V1 equal to I into R1, that is I is 2 ampere, we will calculate it, into R1. R1 value is 30. 2 into 30, 60 voltage. V2 equal to I into R2. I is 2 ohm, 2 ampere into R2 value is 25, that is 50 volt. V3 equal to I into R3. The I value is 2 ampere into 45, 90 voltage. Right? So the potential drop across V1 is 60 voltage, V2 is 50 voltage, V3 is 90 voltage. By adding all this, we got 200 voltage, because the 200 is the applied voltage. So by adding this, we got 200. So the answer what we calculated is correct. So in this problem, we discussed what is the total resistance, then total current and potential drop across each resistor. So in this video, we discussed the three different problems related to the series and parallel combination of resistor. The series and parallel combination of resistor, the derivation available in previous video. Link is available in the description. You can see that. Thank you. Welcome viewers. In this video, we'll see the source transformation, that is current source into voltage source and voltage source into current source. The voltage and current source may be interchanged without affecting the remainder of the circuit. This technique is called a source transformation. We can convert the voltage source into current source into voltage source without affecting the remaining of the circuit. This simplification is needed for the circuit some calculation, so that we are doing the voltage source to current source conversion and current source to voltage source conversion. This is called a source transformation. Any practical voltage source consists of an internal voltage source in series with the internal resistance. So practical voltage source is nothing but voltage source having some internal resistance that is connected in series with the voltage source. So the voltage source in series with the internal resistor is a practical voltage source. Similarly, any current source also having the resistor that is connected in parallel with the current source. Any practical current source consists of an ideal current source in parallel with its internal resistance. So internal resistor available in both voltage source and current source. In case of voltage source, internal resistor is connected in series with the voltage source. In case of current source, the internal resistance is connected in parallel with the current source. Voltage source in series with the internal resistance. Current source in parallel with the internal resistance are called a practical sources. So based on this, therefore any practical voltage source, that is ideal source V and internal resistance R, the voltage source can be replaced by equivalent practical current source. What is practical current source? Ideal source with internal resistance in parallel. So voltage source in series with the internal resistance can be converted into current source in parallel with the internal source, and vice versa is possible, right? So we need to remember that the internal resistor connected in series with the voltage source in parallel with the current source. Based on that, we can go for the transformation. First we will see the voltage source to current source. So the voltage source in series with the internal resistor is connected. This is called a practical voltage source. How will you convert into current source? Current source means the internal resistor is connected in parallel. So voltage source in series with the resistor can be converted, transferred into current source in parallel with the resistor. So this R is equal for both the cases, for voltage source as well as current source. Then how will you find the current I? I equal to V by R. V and R is available. From that we can calculate the current. Current I equal to V divided by R. We will see one example. So here one voltage source is available in series with the internal resistance 3 ohm is there. So this voltage source can be converted into current source in parallel with this 3 ohm internal resistor. So the 3 ohm resistor is now connected parallel. Voltage source is converted into current source. What is this current value? I equal to V by R. V is nothing but 90 voltage. R is 3 ohm. So 90 by 3, 30 ampere. So we calculated the current source value is 30 ampere. Right? So this is the conversion of voltage source to current source. Then we'll go to the current source to voltage source. So current source in parallel with the internal resistance can be converted into voltage source in series with the internal resistance. Right? Then how will you find V? V equal to I into R. I and R values are available. So V can be calculated as I into R. We will see one example. So here 5 ampere current source is available. Internal resistance 3 ohm is connected in parallel. So that can be converted into voltage source in series with the internal resistor 3 ohm. Then how will you find this voltage? V equal to I into R. So I is 5 ampere, R is 3 ohm. So 5 into 3, 15 voltage. Right? So current source in parallel with the internal resistor now converted into voltage source in parallel with, in series with the internal resistance. Now we'll see some more problems. Now we'll see the problem 1. So in this problem there are 3 voltage sources available: 100 voltage, 50 voltage and 60 voltage. For each voltage source the internal resistor also available. This is 1 ohm, 0.5 ohm and 0.8 ohm. So this can be converted into single voltage source and single resistor. How will you find the single voltage and resistor? So the total voltage is nothing but sum of these 3. We can we can find the total voltage from these three sources, 100, 50 and 60. We need to see the polarity. What is the polarity? See here, negative, positive. Here, negative, positive. So these are all connected in series. But while going to here, positive and negative. Right? Polarity now changed. Series mean we need to go like this. Plus, minus, plus, minus, plus, minus, plus mean it is connected in series. We can add. This minus plus minus plus, with these two are added together, 100 plus 50. But while going this third source is plus minus, this polarity is changed, so it is minus 60. Right? These two are connected in series, and but this one is opposing. Right? So 100 plus 50 minus 60. If it is minus plus minus plus minus plus mean it is, we can add it as it is. If any polarity changed, minus plus and plus minus mean we need to subtract. So 100 plus 50, 150, plus from that you have to subtract minus 60 mean 90 voltage. The resultant voltage will be 90. What about the resistor? Resistor we can add as it is, because all resistors are connected in series. So we can add all the resistors. That is 1 ohm, 0.5 ohm and 8 ohm. This 2.3 ohm. So the total resistance will be 2.3 ohm. So this is a problem having 3 voltage source with 3 internal resistor that will be converted into single voltage source and single resistor. Right? The resistors added as it is because it is connected in series. But while finding the total voltage, we need to see the polarity. Right? We need to show the polarity. So these two are same polarity, but here the polarity changed. So this is subtracted. These two are added together. I will go to the second problem. So in this, 3 current sources are available. In the second problem, 3 current sources, 6 ampere, 1 ampere and 2 ampere. In current source mean the internal resistor will be connected in series. This 1 ampere, for this 1 ampere, for this 2 ampere is available. Now we need to convert this current source into single current source and single resistor. How will you find the total current? Total current is nothing but see the direction. So this is upward. This is also upward. This will be downward. So this is rising current, may be taken as the positive current. These two are. This is negative current. So 6 plus 1 minus 2. We can easily identify which one is positive and which one is negative current from the direction. These two are going upward direction. So taken as positive. 6 plus 1. This one is going down. So minus 2. 6 plus 1 7. 7 minus 2 5 ampere. The total current will be 5 ampere. Right? In previous problem, while adding voltage, we see the polarity. In this problem, while adding the current source, we need to see the direction. Based on the direction, we can find. Then what is the total resistance? These two resistors are connected in parallel. So by using the parallel combination, we can find the resistance. We take this is the 1 ohm is R1, 2 ohm is R2. So the total combination while connected in parallel is nothing but R1 R2 divided by R1 plus R2. So 1 into 2 divided by 1 plus 2. 2 divided by 3, 0.67 ohm. Right? The resultant resistance will be 0.67 ohm. Right? So 3 current sources now converted into single current source with a single resistance of 0.67 ohm. Now we'll go to the next problem. So in the third problem, 2 current sources and 1 voltage source is available. In the problem 1, we have 3 voltage sources that will be converted into single voltage source. In second problem, we consider 3 current source that will be converted into single current source. In the third problem, we have 2 current source and voltage source. Both are available. Both current source and voltage sources are considered here. Right. Now we'll convert this entire circuit into single voltage source and single resistor. We can convert to single current source also, right? But in this problem, is converted into single voltage source with single resistor. That is, these 2 voltage sources are converted in, these 2 current sources are converted into voltage source, and final 1 voltage source is reduced. But in another way, we can convert this into current source. We will convert everything into a single current source also. Right. Now, in order to get the single voltage source, now we are going to convert these two current source into single current source. See this direction, both are upward direction, so the total current will be sum of these two, 5 ampere plus 7 ampere, that is 12 ampere. How will you find the resistance? These two resistors are connected in parallel. What is the formula? R1 into R2 divided by R1 plus R2. This R1 is 3 ohm, R2 is 6 ohm. So 3 into 6 divided by 3 plus 6. So 18 divided by 9 is 2 ampere. Right. So these two current sources with two internal resistors now converted into single current source with 12 ampere with the equivalent resistance of 2 ohm. Right. Now we can reduce this diagram. See this. Now it is converted into single voltage, single current source 12 ampere with 12 ampere and single resistor 2 ohm. Right. Now what we have? This one current source available and one voltage source also available. Now our final aim is to find a single voltage source. So now we'll convert this current source into voltage source. How will we convert this current source into voltage source? So the current source in parallel with the resistor can be converted into voltage source in series with the resistor. Right, like this. So it can be converted into voltage source in series with the resistor 2 ohm. So 2 ohm. Then how will you find this voltage V? V is nothing but I into R. I and R is available. Current is 12 ohm, 12 ampere and R is 2 ohm. So 12 into 2, 24. So we can get the 24 voltage here. Right. So 12 ampere with 2 ohm internal resistor now converted into 24 volt in series with the internal resistor of 2 ohm. This 24 is calculated here. Now we have two voltage sources and two resistors that can be easily converted into single voltage source. Now see the polarity. What is the polarity of this circuit? This is plus, minus, plus, plus, minus. Now changed. If it is series mean minus plus, minus plus, minus plus, it will go like that. If it is minus plus, plus minus mean both are opposing. So 24, this 24 minus 10, 14 voltage. The resultant will be 14 voltage. What is the resistor? These two resistors are connected in series. So 2 plus 2, 4 ohm. The resultant resistor will be 4 ohm. Right. So these two resistors opposing these two voltage sources connected in reverse direction, so that 24 minus 10, 14 voltage. These two connected in series, so 2 plus 2, 4 ohm. So this is the final value, simplified diagram. Two current source and one voltage source now converted into single voltage source and single resistor. Right. So in this video we discuss about the source transformation, voltage source to current source to voltage source, the formula, and we discuss the three problem. Thank you. Welcome viewers. In this video we'll see the voltage and current division rule. First we'll see the voltage division rule. Here the two resistors are connected in series, R1 and R2, which is energized by the DC voltage V. So what will happen? This voltage, some of the voltage will be dropped across R1, some of the voltage will be dropped across R2. Depends upon the resistor value. Depends upon the resistor value, voltage will be dropped across R1 and R2. So the voltage across R1 is V1. Voltage across R2 is V2. What is the value? The V equal to V1 plus V2. That is the first formula we need to say. The total voltage applied equal to sum of voltage drop across R1 and R2. Similarly, what is the current? The same current is flowing through R1 and R2. How will you find this V1? V1 equals nothing but current, that current I into R1. V equal to IR. So I is nothing but total current I, R is nothing but R1. Similarly, how will you find V2? V2 equal to I into R2. Based on that, we can find. Now we'll see the description. In the series circuit act as a voltage divider. That is, since the same current is flowing through each resistor, voltage drop are proportional to the value of resistor. So the same current is flowing, but what about the voltage drop? That is depends upon the value of the resistor. So the series circuit means it is act as a voltage divider. Series circuit, the current is same, voltage will be dropped across that. So it is act as a termed as voltage divider. Using this principle, different voltages are obtained from a single source are called a voltage divider. That is, this V equal to sum of V1 and V2. Based on that, we'll go for the derivation. What is the total current I equal to V by R1 plus R2? So this is the total current, that is equal to V by R. V is the applied voltage, R is two resistors available, so R1 plus R2. Right? Then what about V1? V equal to IR, I into R1. V1 means voltage across the resistor R1, so that I into R1. So in this, what is I? You can substitute the I value here. I is nothing but V divided by R1 plus R2 into R1. So this I value is substituted here. So that can be rewrite as V1 equal to R1 divided by R1 plus R2 into V. V1 equal to R1 divided by R1 plus R2 into V. What is this? Voltage across resistor R1 equal to total voltage multiplied by that resistor R1 divided by total resistor. So that is the general formula. The voltage drop across R1 equal to R1 value divided by total resistance into total voltage. From that is the formula. Similarly, V2 equal to I into R2. V2, what is V2? V2 is the voltage drop across resistor R2. So that is equal to I into R2. I is the same current, only one current into resistor. This I can be replaced with this value. I is nothing but V divided by R1 plus R2 into this R2. So R2 divided by R1 plus R2 into V. So voltage drop across the resistor R2 is nothing but the resistor value of R2 divided by total resistance into the applied voltage. Right? So from this we can see the general formula. Voltage drop across the interested branch. That is, which branch is called interested branch is branch resistance. Which resistor we need a voltage drop? That resistance divided by total resistance into applied voltage. Right? So this is the general formula. So voltage drop across interested resistor is nothing but branch resistance divided by total resistance multiplied by applied voltage. So based on that, we'll see one example. See here, the two resistors are connected, 100 ohm and 15 ohm. Sorry, 10 ohm and 15 ohm. It is energized by the DC supply 100 voltage DC supply. They take this 10 ohm as R1, 15 ohm as R2. The voltage drop across R1 is V1, R2 is V2. Now we need to find what is the value of V1 and what is the value of V2 based on the voltage divider rule. So what is the V1? Equal to total voltage, that is applied voltage, multiplied by the resistor value divided by total resistor. Right? So that V1 equal to the total voltage applied is 100 multiplied by 10 ohm. The V1 is nothing but voltage across the 10 ohm. So 10 ohm. Which one we need voltage? That resistor divided by total resistor. 10 plus 15. 10 plus 15. Right? So 100 into 10 divided by 25. So this 4 times available. 4 into 10, 40 voltage. So the voltage drop across V1 is 40 voltage. So by using the voltage divider we calculated. Similarly V2 equal to same thing, total voltage multiplied by resistor of that voltage. Which one we need? That resistor divided by total resistor. So V2 is the voltage across resistor R2. So that here we need to use R2. So V2 equal to 100 into R2 value is 15 divided by 10 plus 15, that is equal to 100 into 15 by 25. So here 4 times. So 4 into 15, 60 voltage. So see this, the sum of these two is 100 voltage because the applied voltage is 100. So in that 40 voltage is dropped across 10 ohm resistor, 60 voltage dropped across 15 ohm resistor. So the less value of ohm, the less voltage will be dropped. For more value of resistor, more voltage is dropped. So sum of these two is the applied voltage. Now we'll go to the current divider rule. So the current division rule, will see that here two resistors are connected in parallel. The previous voltage divider rule, or the resistors are connected in series, then only the voltage will be dropped. For applying the current division rule, the current resistor should be connected in parallel, then only the current will be diverted. Right? So here the voltage V is applied, the total current is I. The two resistors are connected in parallel, R1 and R2. So what will happen? The current will be diverted through R1 and R2. We'll take this is I1, this is I2. So the total current I equal to I1 plus I2. Depends upon the resistor value, sum of the current will diverted through R1, remaining current diverted to R2. So in parallel circuit, the current divides in all the branches. So the parallel circuit acts as a current divider. Previously the series circuit acts as a voltage divider. Here the parallel circuit acts as a current divider. So the total current I equal to I1 plus I2. That is a very basic formula. The total current entering into the parallel branches divided into branch current according to the resistor value. Based on the resistor value, the current will be divided. So we'll go for the derivation. So the basic thing is I equal to I1 plus I2. Total current equal to current flowing through the resistor I1 and I2. So I1 R1 equal to I2 R2 because the potential across both the resistors are equal. So in this diagram, the same voltage is applied through R1 as well as R2. So voltage across R1 is also V, voltage across R2 also V. Only the current is changes. So based on that we can write I1 R1 equal to I2 R2. So from that I2 equal to, bring this R2 here, I1 R1 divided by R2. So based on the voltage drop across both the resistors are equal, we formed this equation. From that we calculated I2. We know that I equal to I1 plus I2. In that you substitute this I2 here. This value is substituted here, so that I1 plus I1 R1 divided by R2. So this I2 is replaced by this value. Now take this I1 common. I1 is available in both the terms. So 1 plus R1 divided by R2. You take the LCM. So here nothing available, so this value will be multiplied here, R2 plus R1. So finally what we got? R2 I equal to I1 plus R1 plus R2. This R2 is multiplied here. This R2 is brought to the numerator. From that, how will you find I1? I1 equal to I into R2 divided by this value, R1 plus R2. I1 equal to I into R2 divided by R1 plus R2. That is, the current through the resistor R1 equal to total current multiplied by another branch resistor. This I1 is the current through R1 resistor. Another branch resistor is R2 divided by total resistor. Right? In case of voltage divider rule, same voltage, we have same resistor we are multiplying, here other branch resistor we are multiplying. That is the difference. So current through resistor R1 equal to total current multiplied by resistor of another branch R2 divided by R1 plus R2. Similarly, we can see the I2 value. So I2 equal to I into R1 divided by R1 plus R2. The current flowing through resistor R2 equal to I into other value of resistor R1 divided by R1 plus R2. So in general we can say current flowing through the interested branch equal to other branch resistor divided by total resistor multiplied by total current. Only here this will be changed. Other branch resistor. In case of voltage same branch resistor. Right. Now we'll go to we'll solve the problem. So in the first problem, the circuit is available. There are three resistors available: 2 ohm, 12 ohm and 6 ohm. From the diagram it is clear these 12 ohm and 6 ohm are connected in parallel. The entire circuit is energized by 12 voltage. Right? So the total current is I ampere through the 2 ohm resistor. At this point the current is divided because of parallel circuit, current divided I1, I2. So in this problem what we need to find the value of I1, I2. This total current flowing through this 12 ohm resistor and 6 ohm resistor. And this is it is marked as point A. This is point A, point B and point C. We need to find what is the voltage across 2 ohm resistor VAB. Then what is the voltage across B and C, this parallel combination. This voltage also we need to find. Right? So 3 resistors available out of 2 resistors connected in parallel. 12 voltage is applied. Total current is I. In parallel the current is divided I1 and I2. We need to find what is the total current, what is the current flow I1, I2, what is the voltage drop across AB and what is the voltage drop across BC. One by one we need to find. First we will simplify this diagram. So these two are connected in parallel. So we will find the equivalent resistance. So in this network 12 ohm and 6 ohm are connected in parallel. We will take this 12 ohm as R1, 6 ohm as R2. Then what is the formula for parallel combination? R equivalent equal to R1 R2 divided by R1 plus R2. R1 is 12 ohm, R2 is 6 ohm. So 12 into 6 divided by 12 plus 6. 72 by 18 is 4 ohm. Now this parallel combination is now converted into single equivalent resistor of 4 ohm. Right? So this 12 ohm and 6 ohm now converted into 4 ohm. Now circuit become very simpler. This 2 ohm and 4 ohm. We can easily see that these 2 and 4 ohm are connected in series. So we can easily find the other values. So the total current I equal to V by R. What is the V? 12 voltage. What is the R value? 2 plus 4. These two are connected in series. 2 plus 4. So 12 divided by 2 plus 4, 12 divided by 6 is 2 ampere. So we easily calculated the value of total current as 2 ampere. Right? I equal to V by R. All values are available. Now we can find the voltage drop across AB. What is the voltage V? V equal to IR, I into R. So VAB equal to I into RAB. So voltage drop across AB is nothing but total current into resistance across AB. So the total current is 2 ampere. The resistance across AB is nothing but 2 ohm. So 2 into 2, 4 voltage. Similarly, voltage across VBC equal to I into RBC. So I is 2 ampere. The resistor across BC, V and C is 4 ohm. So 2 into 4, 8 voltage. So 4 voltages drop across 2 ohm, 8 voltages drop across 4 ohm. The sum of these two, what is the sum? 4 plus 8, 12 voltage. So the 12 voltage, the applied voltage is 12. So the sum of these two also 12. So our answer is correct. Now total current is calculated. Voltage drop across AB, voltage drop across BC also calculated. Now we need to find the I1 and I2. The current flowing through 12 ohm and 6 ohm resistor. Right? So this diagram is drawn again. So this is a diagram what we discussed earlier. 12 voltage is applied. So we calculated the total current is 2 amperes. This 2 ohm and 12 ohm and 6 ohm, this parallel combination available. Now current is divided into I1 and I2. So now we need to find I1 and I2. Other values are calculated. So by using the voltage divider rule, we can find this current divider rule, we can find this I1 and I2. Right? So the total current is 2 ampere, that is divided into I1 and I2. How will you find I1? I1 equal to, what is the formula? Total current multiplied by other branch resistor divided by total resistors. So I1 is the current flowing through 12 ohm. What is the other ohm? Other branch current resistor? 6 ohm. So you have to multiply with 6. Right? So total current is 2 ampere. Other branch resistor is 6 ohm divided by total resistance 6 plus 12, 18. So 2 this divided by 3 times. So 2 divided by 3 ampere. The current flowing through I1 is 2 divided by 3 ampere. So current flowing through 12 ohm resistor I1 is nothing but total current multiplied by other branch resistor divided by total resistor. We need to use this formula. Similarly, current through 6 ohm resistor equal to total current multiplied by other branch resistor 12 divided by total resistance. So that is equal to 2 into 12 divided by 18. Right? So this got cancelled. This 2 and 18 got 9 times. This 9 and 4. This 9 and 12 got this 4 times, is 3 times. So 4 by 3 amps. So the total current will be 4 by 3 amps. So if we add these two, we will get the total current of 2 ampere. So in the current division rule, we need to follow current in any branch equal to total current multiplied by other branch resistor divided by total resistor. Right? So in this problem, we calculated all the value. That is the total current, current flowing through 12 ohm, current flowing through 6 ohm, as well as voltage drop across AB and BC. These values are calculated. Now we'll go to the next problem. So in this problem, we need to find the current through the 10 ohm resistor. So there are 3 resistors available, 15 ohm, 5 ohm and 10 ohm. One current source is available, 5 ampere. So this 5 ampere, what will happen? The current will be diverted through 15 ohm, 5 ohm and 10 ohm resistor. Based on the resistor value, the current will be diverted. So in this problem, what we need to find? We need to find only the current through 10 ohm resistor. Right? Current through 10 ohm resistor is needed. But here 3 resistors available. If you want to find the current division rule, only 2 resistors are there. If it is 2 resistor, we will apply the current division rule. So in order to find this 10 ohm resistor, now we will simplify these two. These two are connected in series, connected in parallel. So we will make it as single resistor. Based on the parallel combination, we will make it as single resistor. That is 15 ohm and 5 ohm are connected in parallel. We will take this 15 ohm as R1, 5 ohm as R2. What is the equivalent resistance? R1 into R2 divided by R1 plus R2. So R1 is 15, R2 is 5. 15 into 5 divided by 15 plus 5. That is 75 divided by 20, 3.75 ohm. Right? So now these two resistors connected in parallel, that is converted into single equivalent resistance, 3.75. Right? Now we can redraw this diagram. So this is a 3.75 ohm and this 10 ohm. Our aim is to find the current through this 10 ohm. See, now only 2 resistors are available. So we can easily apply the current division rule and we can find the current through this 10 ohm resistor. What is the current through this current through this 10 ohm resistor? I2 is termed as I2. That is equal to total current multiplied by other branch resistor. We need a current through 10 ohm resistor, mean we need to multiply with other branch resistor 3.75 divided by total resistance 3.75 plus 10. So I1 equal to total current is 5 into 3.75 divided by 13.75. So that is equal to 1.36 ampere. So current flowing through this 10 ohm resistor is 1.36 ampere. So in this problem, there are 3 resistors available. In that we need to find the current through this 10 ohm resistor. In order to apply the current rule, what we are doing, we are making these two as a single resistor because these two are connected in parallel. So that is make it as single resistor, that is 3.75. After making single resistor, we can easily identify the current through this either I1 or I2. We can easily calculate by using the current division rule. So in this problem, we calculated the current through the 10 ohm resistor. So in this video, we discuss about the voltage division rule, current division rule with the example, and we solved 2 problems based on both current and voltage division rule. Thank you. Welcome viewers. In this video, we'll see the star delta transformation. How the impedances are connected in different configuration. In electrical network, the impedances can be connected in various configuration. The most of these configuration are either star or delta connected network. In general, it is connected either in star connected or delta connected. To solve complex electrical network or simplifying it, we use star delta transformation technique. The complicated network can be, in order to simplify this, we can convert from star to delta or delta to star, so that the circuit becomes simpler. We can go for further analysis. So we need a star delta transformation technique. It replaces any star connected network with its equivalent delta connected network and vice versa. So we can convert star connected network to delta connected or delta connected to star connected. Right? So for simplification, for analysis purpose, we need this conversion technique. First, we will see what is the delta connected network. So this is the delta connected network, that is the resistors are connected, impedance are connected end to end. One end of the resistor connected with another end of another resistor. In delta connected network, it formed by connecting impedances end to end. One end of the resistor is connected to another end of the resistor. So from this we can take the 3 phase. Here named as the term, the corners are named as A, B and C. The resistor values are R1, R2, R3. Resistor connected end to end is called a delta connection. The resistor value R1, R2, R3. Then we'll go to the star connected network. In star connected network, 3 phase wires are connected to a common point. One end of 3 impedances are connected to the common point. From that we can take the neutral. The other 3 terminals are open. So from that we can take 3 phase. So in delta connected, all end to end the resistors are connected. There is no common point, but here one end of all 3 resistors are connected together. That is called a neutral point or common point. The remaining terminals are available. From that we can take the 3 phase. The name is A, B, C. The resistor value is RA, RB and RC. In delta connected, R1, R2, R3. In star connected, RA, RB and RC. Now we'll go to the delta to star transformation. So first transformation we'll see delta to star transformation. This delta connected network can be replaced with the star connected network. R1, R2, R3. Now we are going to replace with RA, RB and RC. Right. In this diagram, the above diagram shows the delta network having terminal ABC with impedance R1, R2, R3. The terminal name is ABC. The resistor value, impedance value is R1, R2, R3. The equivalent star connected network with RA, RB, RC, where they are connected to the corresponding terminals as shown in the diagram. So this R1, R2, R3 is very equivalent to RA, RB, RC. The terminals ABC remain the same, as well as the impedance between them must be the same. So that is based on this principle we are going for a transformation. That is the impedance across the terminals. What is that impedance across the terminals? So the impedance across AB is equal to, in the delta connected network, is equal to the impedance across AB in star connected network also. That is RAB in delta network is equal to RAB in star network, because the terminals are remain same. The impedance between these two terminals in both the delta and star connected network are equal. Based on that, we can go for a transformation. Now we'll start the derivation. Now consider this delta connected network. This one should be replaced with star connected. The term A, B. The total impedance between A and B in the delta network. Only A and B we consider. C we are not considering. We are going to find what is the impedance across AB. So that term C is not available, not applicable. What is the impedance across AB? In between A and B, R1 is connected. But other end, R2 and R3 also connected. This R2 and R3 are series, because C we are not considered. We are considered only AB. So that these two are become a series combination, R2 plus R3. So that is connected in series with, in parallel with the R1. Right. So between A and B we have R1, and this R2 and R3 connected in series, that is in parallel with R1. Right. So that is given here. R1 is parallel with R2 plus R3. Right. So these two are parallel combination. In that one series is available. So the resistance between RAB is nothing but R1 connected in parallel with R2 plus R3. Right. So what is the parallel resistor? R1 R2 divided by R1 plus R2. These two should be multiplied and these two should be added. That is the formula. R1 R2 divided by R1 plus R2. So that R1 into R2 plus R3 divided by R1 plus R2 plus R3. These two resistors multiplied and added. That is the basic formula for parallel resistors. Now we'll go to the next terminal, B and C. Now the same delta connected network, we'll consider this B and C. Previously AB, now B and C. What is the resistance impedance between B and C? See, this R3 is connected. R3. That is in parallel with R1 and R2. Right? This R3 parallel with R1 and R2. We are not consider this point A, because we consider only B and C. So this become a normal terminal. So that this R1 and R2 are connected in series, that is in parallel with R3. So that is given. R3 in parallel with, this symbol is nothing but parallel, R1 and R2, R1 plus R2. Then how will you find the impedance for a parallel combination? That is nothing but multiplication of these two divided by sum of these two. R3 into R1 plus R2 divided by R1 plus R2 plus R3. We take this equation number 2, previous one equation number 1. Now we'll go to the next terminal, next two terminal, total impedance between C and A. First AB, BC, now C and A. Well, C and A, this terminal B is not considered. It's an open normal terminal. What is the resistance impedance between this C and A? R2 in parallel with R1 and R3. R2 in parallel with R1 plus R3. These two are connected in series, that is parallel with R2. What is the equivalent resistance? Multiplication of these two divided by sum of these two. R2 into R1 plus R3 divided by R1 plus R2 plus R3. So take this equation number 3. Now we found the expression for RAB, RBC and RAC based on the delta network. That equations are termed as equation 1, 2 and 3. Now we'll go to the star connected network. The same resistor based on star connected network. What is the resistor? What is the resistance value RAB? What is the resistance connected between RA and B? If we consider A and B, C is not considered. In between A and B, only RA and RB is connected in series. This terminal is open. C is not considered. If a C is not considered, means this will be open. Only this RA and RB are connected in series. So in star network, the resistance between A and B is RA plus RB. The resistance between B and C, these two, that means this is not considered. Only B and C. What is available between B and C? RB plus RC. These two are connected in series. RB plus RC. What about the resistance between RCA, C and A? These two. Then this terminal is not considered. Between C and A, RA and RC is available. RC plus RA. Right? So now we found the expression for RAB, BC and CA in case of star network also. The equations are equation 4, 5 and 6. Now we got 6 equations. First 3 equations based on the delta network. The next 3 equations based on the star network. Right? I think you are able to understand this. RAB means RA and RB are connected in series. This is become open terminal, not considered. Now we'll go for the further simplification. In order to convert, we are adding the equation 1, 2 and 3. What is equation 1, 2 and 3? In case the delta network, RAB plus RBC plus RCA. On other side, what we have? R1 into R2 plus R3 divided by total resistor plus R3 into R1 plus R2 divided by total resistor plus R2 into R1 plus R3 divided by total resistor. This is nothing but equation 1, 2 and 3. Both the sides are added. Now what is the value of RAB, BC from equation 4, 5, 6, that is star connected. We are substituting this value from equation 4, 5, 6. RAB is nothing but RA plus RB. RBC is nothing but RB plus RC. RCA is nothing but RC plus RA. Right? These 3 values are substituted from 4, 5, 6, that is star connected network. Now we'll go to this right hand side. Right hand side, all these 3 are same. So we can take it as LCM, common. R1, R2, R3 is available in all the terms. We can write the remaining terms. R1 into R2 plus R3. R3 into R1 plus R2. R2 into R1 plus R3. Right. Now see this. RA available 2 times. RB available 2 times. RC available 2 times. So we can write 2RA plus 2RB plus 2RC. And here you multiply the terms inside. R1 into R2. R1 into R3. R3 into R1. R3 into R2. R2 into R1. R2 into R3 divided by R1 plus R2 plus R3. Now we'll go for a further simplification. So this is available 2, you can take 2 outside, 2 available in all the time. So 2 times of RA plus RB plus RC. Similarly here R1 R2 available 2 times. R1 R3 available 2 times. R3 R2 available 2 times. So 2 times of R1 R2 plus 2 times of R2 R3 plus 2 times of R3 R1. Right? Here also you take the 2 outside. So this 2 got cancelled. So finally what we have, RA plus RB plus RC equal to R1 R2 plus R2 R3 plus R3 R1 divided by R1 plus R2 plus R3. After all simplification we got this. But what we need, only RA. So this is the delta connected, we need to convert into star connected. So RA is needed. So keep this RA, and RB and RC is brought into right hand side, from left side to right hand side. This RB and RC is brought to the left hand side, right hand side. So it become minus RB RC. So RA equal to this term minus RB plus RC. What is RB plus RC? Can be written as RBC based on the equation 456. Right? Now we have RA, this term minus RBC. So RBC value, this RBC value can be substituted from equation 2. Equation 2, we have the value of RBC. What is that? R3 into R1 plus R2 divided by total resistance. Now see this, one side we have star equivalent resistor. This side we have only delta resistors. So by simplifying this, we can find the value of RA. I will go for the further simplification. So the further simplified as this term minus, that is multiplied inside. Now in the denominator both the values are same, so we can take it as common. Now these terms are written. This R2 R3, this is negative is there, so R2 R3 here, R3 R2 plus, this one is minus and one is plus, so these two got cancelled. Similarly R3 R1, one is plus one is minus, got cancelled. Finally we have only this term, R1 R2 divided by R1 plus R2 plus R3. Now we got the equivalent RA value, star connected network in terms of delta connected network. So similarly we can write the remaining RB and RC. RB equal to R1 R3 divided by R1 plus R2 plus R3 total resistance. Similarly RC equal to R2 R3 divided by R1 plus R2 plus R3. Then how will you remember this value? See this, again this delta connected diagram is available, R1, R2, R3. RA, what is RA? See this RA, this is a A. What are the resistor connected? R1 and R2. So that is available. R1 plus R1 into R2 divided by total resistance. These total resistance are common. Similarly RB, this is terminal B. What are the resistors available? R3 and R1. That is multiplied. You can easily remember. Similarly RC, this terminal C. What are the resistors available? R2 and R3. So that R2 by R2 into R3 divided by total resistance. So RA means what are the resistor connected? You have to multiply. You can easily remember. Now we converted delta to star. Now we'll go for the star to delta conversion. So in this, these three are taken as equation 7, 8 and 9. So from this 7, 8, 9 only we can proceed for further simplification, further transformation, right? Already we have 6 equations. Now this is 7, 8 and 9. Now we'll go to the star to delta transformation. Delta to star is completed. We'll go to star to delta conversion. So now we have already 9 equations are available. In order to find the equivalent delta resistance, multiply equations 7 and 8. Already we have 7, 8, 9, 3 equations available, RA, RB, RC. In that we are multiplying equations 7 and 8, RA and RB. So these terms are available. So denominator both are same. So R1 plus R2 plus R3 is the whole square. Here R1, R2, R1, R3. R1 available 2 times. So R1 square, R2, R3 divided by total resistance square. This is equation number 10. Now multiply equation 8 and 9, RB and RC. RB and RC. Same thing. these two are same, so that R1 plus R2 plus R3 the whole square. Here R1, R3, R2, R3. R1, R3, R2, R3. R3 available 2 times. So R1, R2, R3 square. So this take this equation as 11. Previous one, equation number 10. Now multiply the equations 7 and 9. Multiply the equations 7 and 9. RA and RC. So the denominator same, R1 plus R2 plus R3 the whole square. Here available R1, R2, R2, R3. So R2 available 2 times. So R1, R2 square into R3. This equation number 12. Now we got equation number 10, 11 and 12. That is RA, RB, RB, RC, RC and RA. These 3 equations are we framed. Now we'll go for the further simplification. Now we are going to add these 3 equations. Equation 10, 11 and 12. What we framed now earlier, we are going to add. That is RA, RB plus RB, RC plus RC, RA. Then these 3 terms. The denominator same. Total resistance square. Here R1 square is there. Here R3 square is there. Here R2 square is there. So denominators are equal. So we can take it as common. We can write all these 3 terms. So in this R1, R2, R3 available in all the 3 terms. Only here R1 square, R2 square, R3 square. So R1, R2, R3 available in all 3 terms taken as outside. So while taking R1, R2, R3, what will happen here? R1 is available. Here R2 is available. Here R3 is available. Remaining. So R1, R2, R3 taken outside, the remaining values are written. So this is, both are same. So one term got cancelled. This one term got cancelled. So after that what we have? RA, RB plus RB, RC plus RC, RA equal to R1, R2, R3 divided by R1 plus R2 plus R3. After simplification, we got this value. Now we are going to rewrite this. How we are rewriting? R1, R2 divided by R1 plus R2 plus R3, and this R3 is written separately. Right? This R1, R2 written here, R3 written separately. What is this R1, R2 divided by R1, R2 plus R3? From equation 7, this R1, R2 divided by R1 plus R2 plus R3 is nothing but RA. You can refer from equation 7. So this term can be replaced as RA. Right? Now bring this RA in the denominator, so that R3 equal to this term divided by RA. So that we can write R3 equal to RA, RB plus RB, RC plus RC, RA divided by RA. It is interchanged. So based on this value, we can write R2 and R1 values also. So the numerator is same for all the 3 terms. Only in R3 we need to multiply, divide by RA. R2 divided by RB. R1 divided by RC. That also we'll see in the diagram. How will you identify? R3 means RA. R2 means RB. R1 means RC. That also we'll see. So now we completed the star to delta conversion also. Now we'll summarize this. So after 2 transformation completed, just we'll summarize all this. This is a delta connected network. R1, R2, R3 is available. It's a star connected network. RA, RB, RC is available. Right? Now we formed the 2 transformation we completed. This is a value R1, R2, R3 in terms of star connected. RA, RB, RC in terms of delta connected. Right? So this one I already explained how to find the RA. RA means in the terminal A, this R1 and R2 is available. From that easily identify. Similarly, how will we find this R1? R1 equal to, what is R1? Where is this available? In between A and B. Similarly, what is available in between A and B? RA and RB. You have to refer the another terminal, other terminal resistance, RC. Right? So the R1 means RC. How we can easily remember, R1 is connected between A and B. So in between A and B, what we have? RA and RB. The rest of the resistor is RC. So the rest of the resistor you have to divide. By that you can easily remember, right? So we have all two type of transformation completed, star to delta and delta to star. So in this, suppose if all resistors are equal, right, in star connected, RA equal to RB equal to RC equal to R star, then what will happen? R delta equal to 3 times of R star. So if you substitute in the previous equation, you can easily found this, you can easily remember. R delta, if all resistors are equal, R delta equal to 3 times of R star. Suppose delta, all resistor in the delta connector network is same, R1 equal to R2 equal to R3 equal to R delta, means the R star equal to R delta divided by 3. That is based on the expression we calculated. So you can easily remember, right? If all resistors are equal, you can use this formula. So in this video we discuss what is the transformation, what is the star connected network, what is the delta connected network, then delta to star transformation, then star to delta transformation, then summarize, and what are the, if all the resistors are equal, what is the equivalent value. These things are discussed. Thank you.